Look up at the night sky, past the familiar pinpricks of stars, and try to picture a galaxy unlike any other. Not a swirling spiral or a featureless ellipse, but a perfect circle of brilliant blue stars, encircling a golden core like a celestial wedding band suspended in the velvet black of space. This is not an artist's impression. It is a real place known as Hoag's object, and it is just one example of one of the universe's most baffling and beautiful creations, the Ring Galaxy. What if I told you that within these cosmic rings, these elegant loops of starlight, lie mysteries so profound they challenge our very understanding of physics itself? These are not serene, static structures. They are cosmic crime scenes, gravitational whirlpools, and windows into the most violent and creative forces shaping our universe. Today, we are embarking on a journey to explore 50 of the strangest phenomena found within these unique galactic structures. This is not just a catalogue of weird facts. It is a voyage to the frontier of modern astronomy, where the rules we think we know begin to bend and break. We will uncover galaxies that are impossibly ancient, discover star-forming regions that defy logic, and grapple with gravitational anomalies that hint at physics beyond Einstein. Each ring tells a story of cataclysmic collisions, of delicate balances between creation and destruction, and of secrets that have been hidden in plain sight for billions of years. So prepare to have your perspective shifted. We are about to dive deep into a cosmic mystery that is as beautiful as it is bizarre, exploring 50 clues that astronomers are using to piece together the true nature of these enigmatic rings. This is a journey for the curious, for those who look at the stars and not only wonder what they are, but how they came to be. The answers, as we will see, are often stranger than anything we could have imagined. Our journey begins with perhaps the most striking feature of all, the perfect, almost artificial-looking symmetry of these cosmic rings. When you first see an image of a galaxy like Hoag's object or the so-called Cartwheel Galaxy, the immediate question that springs to mind is how. How can nature, with all its chaotic forces and random events, produce something so geometrically flawless? This isn't the messy, spiral-armed whirl we see in our own Milky Way. This is a precise circle of brilliant blue, newborn stars encircling a central, older core, like a diamond set within a sapphire band. This perfect ring symmetry is the first great puzzle, and its explanation points to some of the most violent events in the cosmos. The leading theory astronomers have pieced together involves a catastrophic galactic collision. Imagine two galaxies, each containing hundreds of billions of stars, passing through or near one another. In most cases, this results in a tangled, irregular mess. But under very specific conditions, a precise, head-on collision, like a bullet hitting a bullseye, something extraordinary can happen. The gravitational shockwave from the smaller intruder galaxy passing directly through the center of a larger disk galaxy sends ripples racing outward through the gas and dust, much like a pebble dropped into a pond. This wave compresses the interstellar material, triggering a colossal burst of star formation precisely at the outer edge of the disturbance. What we see as that beautiful, symmetric ring is actually the firestorm of millions of stars being born in this propagating wave. A stunning example of this is the galaxy known as AM 0644741, often called the Lindsay-Shapley ring. Here, we see the aftermath of such a cosmic bullseye hit. The smaller intruder galaxy has already passed through and is now receding into the distance, but its gravitational fingerprint remains etched into the larger galaxy in the form of a nearly perfect blue ring of intense stellar nurseries. The symmetry is so precise because the collision was so direct. The force was applied evenly in all directions from the center, creating that circular wave. This process also explains the youthful blue hue of the ring stars. They are massive, hot, and short-lived, telling us the collision was a relatively recent event in cosmic terms. But head-on collisions are rare. This leads to an alternative and perhaps even more fascinating idea: intrinsic instability. Some astronomers propose that certain disk galaxies could develop a ring from within without any external trigger. Instabilities in the galaxy's own gravitational field or in the complex dynamics of its central bar structure could, over eons, funnel gas outward to a specific resonance radius, where it accumulates and ignites into a ring of star formation. This would be a slower, more graceful dance compared to the violent ballet of a collision, creating a ring that is just as symmetric but born from the galaxy's own internal rhythm. The challenge is distinguishing between these origins, as the end result can look remarkably similar, forcing us to look for subtler clues in the motions of the stars and the composition of the ring itself. This quest to understand ring symmetry is far more than an academic exercise. It tells us that galaxies are not isolated, island universes. They are dynamic systems that grow, change, and sometimes rebuild themselves through immense transformative violence. The perfect ring is a cosmic fossil, preserving the memory of a single, defining cataclysm that reshaped an entire galaxy. It shows us that from the most destructive events can spring the most beautiful and ordered structures, a theme that echoes throughout the cosmos. This flawless geometry, whether forged in a sudden impact or a slow internal pulse, stands as a testament to the powerful and often surprising laws of physics that govern the universe on its very largest scales. Now, let's shift our gaze from the ring itself to the very heart of these galaxies, where we encounter a second, equally baffling mystery. In a typical spiral galaxy like our own Milky Way, the graceful arms spiral inward to meet a distinct glowing central hub, a dense swarm of older yellow stars known as the galactic bulge. It's a fundamental component, a core feature in our standard models of how galaxies assemble and evolve over billions of years. But look closely at a pristine ring galaxy like Hoag's object. That central region is there, glowing softly, but it lacks that classic puffed-up bulge. Instead, we see what appears to be a more isolated, almost detached core of stars. This absence of a traditional central bulge isn't just a minor detail. It's a direct challenge to our understanding of galactic anatomy. Why is this so strange? Because the bulge is thought to be one of the first parts of a galaxy to form. In the primordial universe, vast clouds of gas and dark matter collapsed under their own gravity, and stars began to form in a frantic, chaotic burst. This process naturally created a dense central concentration, the seed of the bulge. Later, the remaining gas settled into a spinning disk around it, forming the spiral arms. So, finding a mature galaxy without a significant bulge is like finding a fully grown animal that somehow skipped developing a spine. It forces us to ask a critical question. Did this galaxy never form a bulge in the first place, or was its bulge somehow removed or disrupted by the same cataclysmic event that created the ring? This is where the collision theory we discussed earlier offers a tantalizing possibility. The violent head-on impact of a smaller galaxy might not only trigger the ring of star formation, it could also profoundly disrupt the larger galaxy's core. The incredible gravitational forces involved could literally scatter the stars of the central bulge, smoothing them out into a more diffuse and less concentrated structure. Alternatively, the intruder galaxy's passage might have funneled a vast amount of gas away from the center, starving the core of the material needed to form and sustain a prominent bulge. In this scenario, the missing bulge becomes another piece of evidence pointing to a past galactic trauma. But the implications run even deeper, touching on one of the greatest mysteries in all of cosmology: dark matter. We believe that every galaxy is embedded within a massive, invisible halo of this mysterious substance, and its gravitational pull is what holds the galaxy together. The distribution of dark matter is thought to be closely tied to the visible structure of the galaxy, with the highest density coinciding with the central bulge. So if the visible bulge is absent or altered, what does that tell us about the invisible dark matter halo? Has it been disrupted as well, or does its distribution no longer match the visible stars? Studying the motions of stars in these bulgeless ring galaxies provides a unique laboratory for testing our models of dark matter, potentially revealing that its behavior is even more complex than we currently assume. The dynamics within these galaxies are consequently unlike anything we see in a standard spiral. Without a massive central gravitational anchor, the orbital dance of stars and gas in the ring may follow different rules. The entire system might be more fragile, more susceptible to external gravitational tugs from nearby galaxies, or even prone to developing new instabilities over time. This missing central feature forces a complete re-evaluation of the gravitational engine at the heart of the galaxy. It suggests that the elegant, simple picture of galaxy formation we once held is incomplete. Ring galaxies, with their beautiful symmetry and perplexingly empty centers, are showing us that the universe has more than one way to build an island of stars, and some of those methods are far more dramatic and disruptive than we ever imagined. This brings us to one of the most spectacular sights in the cosmos, a phenomenon that turns these elegant rings into the universe's most brilliant fireworks displays. We've seen how a gravitational shockwave can carve out a perfect circle, but that wave does something even more incredible. It ignites a firestorm of creation. While the central core of a ring galaxy often glows with the steady, aging light of older stars, the ring itself is a searing, brilliant blue. This color is a direct telltale sign of a cosmic baby boom, a frenzied burst of star formation happening on a scale that is almost incomprehensible. The ring isn't just a structure, it's a stellar nursery of epic proportions, and the engine driving this birth is the relentless compression of the density wave. Think of a vast, quiet cloud of interstellar gas and dust drifting peacefully for eons. Then, a tsunami of gravitational force, the density wave from the collision, sweeps through. This wave doesn't just pass by, it violently squeezes the gas, dramatically increasing its density. When you compress a gas cloud, you push its particles closer together. At a certain threshold, this increased density overwhelms the cloud's internal pressure, and pockets of gas begin to collapse under their own gravity. Each collapsing knot becomes the seed of a new star. This process, triggered all along the circular wavefront, results in a chain reaction of star birth, lighting up the entire ring in a blaze of youthful energy. It's a case of cosmic violence giving rise to vibrant new life. The stellar population born from this frenzy is unlike the mixed generations found in a typical galaxy. Here in the ring, the stars are almost all newborns. We see a spectacular concentration of O and B-type stars. These are the rock stars of the stellar world. They are immensely massive, many times larger and hotter than our own sun. They burn their nuclear fuel with a ferocious intensity, shining with a brilliant blue-white light and living fast, dying young in spectacular supernova explosions after only a few million years. Their collective luminosity is so immense that it dominates the light of the entire galaxy, making the ring the undeniable center of attention. Scattered throughout this blue ring are some of the largest and brightest objects in the known universe, massive H2 regions or emission nebulae. An H2 region is a vast cloud of hydrogen gas that has been heated to a glowing, pinkish-red state by the intense ultraviolet radiation pouring off nearby newborn supergiant stars. These are not just pretty clouds, they are the very cradles where stars are actively forming. Within them, you can often find pillars of denser gas and dust being sculpted and eroded by stellar winds, with new protostars igniting inside. In a ring galaxy, these H2 regions are not just present, they are colossal, often spanning hundreds of light years across. They dot the ring like glowing pearls on a necklace, each one a testament to the ongoing, furious pace of creation. This concentration of star formation in the ring alone creates a stark and fascinating dichotomy. The galaxy's center, as we discussed, is quiet and aging, while its outer edge is a maelstrom of youth and activity. This spatial segregation is a direct snapshot of the galaxy's history, frozen in time. By studying the exact age and distribution of the stars in the ring, astronomers can essentially carbon date the collision event itself. The ring acts as a cosmic clock, telling us when the galactic bullseye happened. Furthermore, this burst of star formation doesn't last forever. As the massive stars quickly die in supernova, they blast the surrounding space with heavy elements forged in their cores and in their violent deaths, enriching the galaxy with the building blocks for future planets and potentially life. The ring galaxy, in its beautiful and transient blue phase, is not just a static picture. It is a dynamic ecosystem, a single, glorious chapter in the long and evolving story of a galaxy reborn from catastrophe. And right beside this cosmic nursery, this frantic burst of youthful energy, lies a scene of profound quiet. If the ring is a roaring concert, the central core is a silent library. This stark contrast is one of the most defining and puzzling features of a ring galaxy. While the outer ring blazes with the blue light of newborn supergiants, the core glows with a soft, warm, golden light. This color is the signature of an entirely different stellar population, ancient, cooler stars, similar to our own sun but billions of years older. They are the quiet elders of the galaxy, and their presence tells a story of a much calmer, far more distant past. This lack of recent star formation in the very heart of the galaxy is a significant clue. In a typical spiral galaxy, the central regions are often bustling with activity. Gas can be funneled inward by the spiral arms or a central bar, leading to ongoing, if not intense, star birth. But in many ring galaxies, the core appears strangely dormant, almost fossilized. Telescopes searching for the telltale signs of youthful stars, the ultraviolet glow or the presence of those pink H2 regions, often find the center to be a relative desert. The question is, why has the star-making machinery in the core shut down? Astronomers see this quiet core as a relic, a preserved remnant of the original galaxy that existed before the Great Collision. The leading theory suggests that the cataclysmic event that created the ring was so specific in its violence that it selectively targeted the galaxy's outskirts. Imagine the smaller intruder galaxy passing directly through the center like a ghost. Its gravitational pull would have been immense, but its effect on the densely packed stars in the core may have been minimal. Stars are mostly empty space, so a direct hit is incredibly rare. The core's stars would have been violently shaken but not torn apart. The real victim was the galaxy's gas reservoir. The collision's gravitational shockwave would have acted like a giant plow, scooping up the diffuse gas and dust that was spread across the galactic disk and pushing it outward into that expanding ring. This effectively robbed the core of the raw materials needed to form new stars, stranding the ancient stellar population and cutting off their future generations. This creates a fascinating celestial dichotomy. We are essentially looking at two galaxies in one, a preserved antique at the center and a brand new dynamic structure at the edges. By studying the properties of the core stars, their age, composition, and motion, we can peer back in time to understand what the progenitor galaxy was like. Was it a grand spiral similar to the Andromeda galaxy, or was it a different type of disk galaxy altogether? The quiet core holds those answers, acting as a cosmic archive. The implications of this separation extend to the galaxy's future. With star formation dead in the center and raging only in the ring, the galaxy is evolving in a profoundly lopsided way. The massive stars in the ring will live short, dramatic lives, exploding as supernova within a few tens of millions of years. These explosions will blast the remaining gas out of the ring, potentially shutting down star formation there as well. What will be left? A golden, aging core surrounded by a fading ring of lower mass, longer-lived stars. Over billions of years, the brilliant blue ring will turn yellow and then red as the brightest stars die off, and the entire structure may eventually resemble a peculiar elliptical galaxy. The ring galaxy, in its current spectacular form, is therefore a transient phase, a brilliant but fleeting rebirth following a galactic near-death experience. This quiet core isn't just a relic of the past, it is the seed from which the galaxy's next evolutionary chapter will grow, a patient elder waiting for the fireworks to subside. Just when you think ring galaxies cannot get any stranger, the universe presents us with a configuration that seems to defy all common sense, the polar ring galaxy. Picture everything we have discussed so far, a central core, a surrounding ring, and then tilt that ring a full 90 degrees. Instead of orbiting in the same flat plane as the main galaxy, like a record spinning on a turntable, this ring stands on its edge, circling the poles of the galactic core like a Ferris wheel rotating around a central hub. This bizarre perpendicular arrangement creates a structure that looks less like a celestial object and more like a piece of cosmic engineering, a celestial cartwheel of staggering proportions. A perfect example of this cosmic oddity is the galaxy known as NGC 4650A. Through a powerful telescope, it appears as two distinct galaxies impossibly merged into one. At its heart lies a central lenticular galaxy, a lens-shaped collection of older, yellowish stars, but encircling this core, oriented almost perfectly perpendicular to it, is a massive, bright ring brimming with young blue stars, glowing gas, and dark lanes of dust. The effect is breathtaking and disorienting. It challenges our ingrained sense of how celestial objects should align. This is not a simple flat disk. It is a three-dimensional structure of immense scale and complexity. The very existence of such a galaxy poses a profound dynamical puzzle. How can a vast structure like a ring, containing billions of stars and immense clouds of gas, maintain a stable orbit that is perpendicular to the main galaxy? The forces at play are incredibly delicate. For a polar ring to form and persist, it must be in a state of near-perfect balance, orbiting within the gravitational field of the main galaxy's invisible dark matter halo. This halo is thought to be roughly spherical, and the polar ring likely orbits within a specific, stable path dictated by this spherical distribution. It is a cosmic tightrope act where the ring's motion is a precise dance between the pull of the central core and the overarching gravity of the dark matter that envelops the entire system. The leading theory for how such a bizarre structure arises involves another tale of galactic cannibalism, but with a unique twist. The most plausible scenario is that a smaller, gas-rich dwarf galaxy ventured too close to a larger lenticular galaxy. Instead of a head-on collision, this was a graceful yet destructive galactic merger. The dwarf galaxy was likely captured and then torn apart by tidal forces, its stars and gas stretched into a long stream. Over billions of years, this stream of material settled into a stable orbit that happened to be perpendicular to the larger galaxy's plane, eventually coalescing into the brilliant ring we see today. This process suggests that polar rings are not born from a single violent impact, but from a slower, more drawn-out act of cosmic consumption and digestion. Studying these galaxies provides astronomers with a rare and invaluable opportunity. Because the polar ring orbits around the poles of the main galaxy, we can use the motion of its stars and gas to map the three-dimensional shape of the galaxy's dark matter halo. By measuring how fast the ring is rotating at different distances from the core, scientists can essentially weigh the invisible dark matter and determine its distribution in a way that is impossible for a flat galaxy. Polar ring galaxies are, therefore, not just curiosities. They are natural laboratories for probing the most mysterious substance in the universe, offering a unique window into the hidden architecture that binds galaxies together. This elegant dance of rings and cores leads us directly to one of the most profound mysteries in all of modern cosmology, a puzzle that lies not in the light we see, but in the invisible scaffolding that holds these galaxies together. When astronomers point their telescopes at a ring galaxy, they are not just capturing a beautiful image, they are measuring the subtle motions of stars and gas to weigh the galaxy. They do this by analyzing the galaxy's rotation curve, a graph that plots how fast material is orbiting at different distances from the center. And what they find in many ring galaxies is deeply puzzling, challenging our most fundamental ideas about the universe's hidden architecture, the nature of dark matter. In a typical spiral galaxy, the rotation curve tells a very specific story. According to the laws of gravity, stars and gas on the outer edges, far from the central mass, should orbit much more slowly, just as Pluto orbits the Sun far more sluggishly than Mercury. But for decades, observations have shown this isn't the case. The orbital speeds in the outer reaches of spiral galaxies remain high instead of dropping off. This was the first major evidence for dark matter, the idea that galaxies are embedded within vast, invisible halos of some unknown substance whose gravity provides the extra pull needed to keep those outer stars whipping around so fast. Now apply this same reasoning to a ring galaxy. The brilliant ring of stars is often the outermost visible structure. By measuring the speed of this ring as it orbits the core, astronomers can take a critical measurement of the galaxy's total mass at that great distance. But here's where the anomaly appears. In some ring galaxies, the rotation curve doesn't just stay flat. It behaves in unexpected ways. The ring might be moving far too quickly, suggesting an overabundance of dark matter concentrated in the ring's vicinity. Or in other cases, the ring's motion might be too slow, implying a puzzling deficit or an oddly shaped distribution of the invisible halo. This is the core of the mystery. The observed motion of the ring often implies a distribution of dark matter that simply doesn't match the standard, smooth, spherical halo models that work for other galaxy types. One compelling explanation for these anomalies points back to the violent formation history we've already discussed. The cataclysmic collision that created the ring didn't just rearrange the visible stars and gas, it must have also profoundly disturbed the galaxy's dark matter halo. Imagine the gravitational shockwave from the impact sending ripples not only through the star-forming gas, but also through the very fabric of the dark matter. This could have caused the dark matter to slosh around, becoming denser in some regions and thinner in others, creating a lumpy or distorted halo that no longer fits our standard models. The ring, orbiting within this disturbed gravitational landscape, then moves in a way that seems anomalous to us, but is actually a direct tracer of this invisible turmoil. Another, even more radical possibility is that we are seeing hints of something beyond the standard understanding of dark matter. Most models assume dark matter particles only interact with each other and with normal matter through gravity. But what if that's not entirely true? What if dark matter particles can interact with each other through some other unknown force? In the extreme conditions of a galactic collision, this could cause the dark matter to behave more like a fluid, with friction and pressure effects that alter its distribution in ways that collisionless models cannot predict. The strange rotation curves of ring galaxies could be the first observational clues pointing toward this self-interacting dark matter, a concept that would revolutionize particle physics. This makes ring galaxies absolutely invaluable natural laboratories. Their unique geometry provides a clear, isolated track, the ring itself, on which to measure gravitational effects. Unlike a messy spiral galaxy where arms and bars complicate the picture, the ring offers a pristine test case. By meticulously mapping its rotation and comparing it with sophisticated computer simulations of galactic collisions, astronomers can run a cosmic experiment. They can test different models of dark matter by seeing which one, when plugged into the simulation, produces a virtual ring galaxy that rotates exactly like the real ones we observe. Each anomalous rotation curve is therefore not a problem to be dismissed, but a precious piece of data, a key that could eventually unlock the true nature of the invisible substance that makes up most of the mass in the universe. But the gravitational influence of a ring galaxy can reach out across the cosmos in an even more direct and mind-bending way. We've discussed how their mass, both visible and dark, dictates the motion of stars within them. Yet, according to Einstein's theory of general relativity, mass doesn't just dictate motion. It actually warps the very fabric of space and time around it. And when an object is massive enough, this warping can act like a lens, bending the path of light itself. This leads us to a phenomenon where these ring galaxies become more than just objects of study. They transform into the universe's own powerful telescopes. Some ring galaxies, by pure cosmic chance, are positioned perfectly in space to act as gravitational lenses, magnifying the faint glow of galaxies that lie billions of light years behind them. The mechanics of this are as elegant as they are strange. Imagine a ring galaxy sitting between our telescopes and an incredibly distant, faint galaxy from the early universe. The immense combined mass of the ring galaxy's stars, gas, and its extensive dark matter halo creates a deep gravitational well in spacetime. As light from the background galaxy travels toward us, it passes through this warped region. Instead of traveling in a straight line, the light bends around the foreground galaxy. From our perspective, this distortion can magnify and amplify the background object's light, making the faint appear bright. Even more strikingly, it can create multiple images or stretch the distant galaxy into a perfect, luminous arc, a cosmic mirage known as an Einstein ring, a beautiful and rare confirmation of relativity on a galactic scale. What makes a ring galaxy a particularly interesting lens is its unique mass distribution. Unlike an elliptical galaxy, which has a smooth, concentrated mass profile, a ring galaxy's mass is distributed in a very specific way, a dense central core surrounded by a massive ring. This complex structure can create more intricate lensing effects than a simpler galaxy might. Instead of just a single arc or a pair of images, the lensing effect might produce multiple, distorted images of the same background object arrayed around the ring. This complexity is actually a benefit for astronomers, as it provides more data points to model the precise distribution of mass, both visible and dark, within the ring galaxy itself. By analyzing how the light is bent, scientists can create a detailed map of the lensing galaxy's gravitational field, offering an incredibly precise way to weigh it and probe the shape of its dark matter halo. The scientific value of this natural telescope is immeasurable. The background galaxies being magnified are often so far away that their light has been traveling for more than 90% of the universe's history. Without the gravitational lens, they would be far too faint and small for even our most powerful observatories like the James Webb Space Telescope to study in any detail. But the lensing effect, sometimes magnifying their light by a factor of 10 or more, acts as a free zoom lens, allowing us to peer into the era of the first galaxies. We can study their rate of star formation, their internal structure, and their chemical composition in a level of detail that would otherwise be impossible. Each ring galaxy that functions as a lens gives us a precious window into the infant universe, helping us understand how galaxies assembled themselves in the cosmic dawn. This phenomenon beautifully ties together the violent history of the ring galaxy with the grand narrative of cosmic evolution. The same catastrophic collision that forged the brilliant ring also shaped the mass distribution that now allows it to serve as a cosmic lens. We are using a relatively recent, transient structure, the ring itself, as a tool to see back to some of the oldest objects in existence. It's a perfect example of the interconnectedness of the cosmos, where one galaxy's dramatic rebirth provides the very key to unlocking the secrets of another's infancy. The ring galaxy, in this role, is no longer just a subject of curiosity. It becomes an active partner in our exploration, a natural observatory that expands our view to the very edges of space and time. And if you thought polar rings were the ultimate twist in galactic structure, wait until you see a galaxy that looks like it was built by a celestial wheelwright. The Cartwheel Galaxy is arguably the most famous ring galaxy in the universe, a poster child for cosmic collisions. Its namesake structure is almost unnervingly perfect, a brilliant blue outer ring surrounding a bright, diffuse inner ring, all set against a backdrop of faint, wispy filaments. But if you look closely, especially with the penetrating gaze of a telescope like Hubble, you'll notice something that breaks the perfect symmetry: faint radial streaks like the spokes of a wagon wheel connecting the inner hub to the outer rim. These are not mere artifacts of the image, they are real structures, and their origin is a key piece of the puzzle in understanding the galaxy's violent history. So, what exactly are these enigmatic spokes? They appear as lanes of dust, gas, and perhaps older stars, stretching outward from the central core region through the quieter inner ring and reaching toward the frenzied star-forming outer ring. Their presence is crucial because a perfect, symmetric density wave from a collision might be expected to produce a clean, empty space between the core and the ring. The spokes show that the aftermath is far more complex. They are the scars of the impact, the lingering evidence of the galactic structure that existed before the cataclysm. One leading theory suggests they are the ghostly remnants of the progenitor galaxy's spiral arms. Before the collision, this galaxy was likely a normal spiral, much like our own Milky Way. When the smaller intruder galaxy passed through its center, the gravitational shock wave would have thrown the entire system into chaos. While the wave triggered star formation in a neat outer ring, the pre-existing spiral arms could have been stretched, shredded, and partially preserved as these radial streaks, frozen in time as a skeletal reminder of what once was. Another compelling explanation involves the very propagation of the density wave itself. Think of the collision not as a single, clean event, but as a series of complex gravitational interactions. The initial shockwave might not have been a perfectly smooth, expanding circle. Instabilities in the wave as it traveled outward through the galactic disk could have caused it to develop ripples or irregularities. These imperfections might have focused material into these radial spokes, much like how wrinkles in a sheet can channel water into streams. In this scenario, the spokes are not ancient relics but dynamic features formed by the collision process, acting as channels along which gas and dust are still flowing from the inner regions of the galaxy toward the active star-forming front at the outer ring. The Cartwheel Galaxy provides a spectacular test case for these ideas. Observations show that the spokes are not uniform, they are patchy and intertwined with the galaxy's intricate structure. Some appear darker, dominated by dense dust that obscures the light from stars behind it. Others seem brighter, suggesting they contain populations of stars that either survived the collision or formed in situ along these cosmic filaments. By studying the composition and motion of material within the spokes, astronomers can distinguish between the two theories. If the stars in the spokes are very old and their motion aligns with what would be expected from former spiral arms, the relic theory gains strength. If, however, the material is flowing outward and is actively involved in the ongoing star formation, the dynamic wave theory becomes more plausible. It's even possible that both processes are at work, with pre-existing structures being reshaped and amplified by the propagating wave. Understanding these spokes is about more than just explaining a curious visual feature. They hold the key to the transfer of mass and energy across the galaxy. They might be the pathways through which the galaxy is redistributing the remaining fuel for star formation. Gas funneled along these spokes from the inner regions could eventually reach the outer ring, providing fresh material to sustain the stellar baby boom for millions of years longer than if the ring were isolated. This would mean the galaxy's rebirth is a more prolonged and interconnected process. The spokes transform our view of the cartwheel from a simple two-part structure a core and a ring, into a complex, interconnected system where the past and present are dynamically linked. They are the enduring threads weaving together the story of the galaxy's destruction and its spectacular, ongoing rebirth. Yet the cosmos holds even more peculiar combinations where two seemingly contradictory galactic traits exist side by side. We've explored massive, brilliant rings forged in violent encounters, but what about rings that form around galaxies that are barely there at all? This brings us to the deeply puzzling case of ultra-diffuse galaxies that somehow possess ring structures. Imagine a galaxy as wide as the Milky Way, but containing so few stars that it is almost transparent, a ghostly whisper of a galaxy against the dark backdrop of space. These are ultra-diffuse galaxies, or UDG, and the notion that one could host a distinct ring seems to defy the very logic of how rings are made. The primary challenge lies in the proposed nature of these faint giants. The leading theory suggests that ultra-diffuse galaxies are incredibly rich in dark matter. This vast, invisible halo acts as a gravitational anchor, stabilizing the galaxy and preventing its sparse population of stars from being easily disrupted. They are thought to be serene, stable, and ancient systems. This stability is precisely what makes the presence of a ring so problematic. Our standard model for ring formation relies on a violent head-on collision, a bull's-eye impact that sends a density wave rippling through the galactic disk. But for a UDG, such an event should be nearly impossible. Its stars are so widely spaced that a direct hit from another galaxy is astronomically unlikely. It would be like trying to strike a specific dandelion seed floating in an empty sports stadium with a single grain of sand. Even if a collision did occur, the galaxy's dominant dark matter halo should absorb the shock without triggering the clean, symmetric star-forming wave we see in a classic ring galaxy. So, if a collision is off the table, how does a ring appear around such a faint ghost? Astronomers are investigating several intriguing alternatives. One possibility is that these rings are not the product of a recent cataclysm, but are instead primordial relics. Perhaps during the galaxy's formation billions of years ago, a complex interplay of gas dynamics and dark matter created a stable ring of gas that has only recently and very slowly begun to form stars. This would make the ring an inherent part of the galaxy's structure since its birth, not a later addition. Another, more dynamic idea involves a very slow, gentle interaction. Instead of a dramatic collision, a nearby dwarf galaxy could have had a prolonged gravitational dance with the UDG over billions of years. This slow tidal pull might have ever so gradually stirred the UDG scant gas, coaxing it into a ring-like configuration without the need for a violent impact. This process would be so subtle that it wouldn't disrupt the galaxy's overall stability. The existence of these ringed UDGs forces a critical re-examination of the dark matter hypothesis itself. If these galaxies are indeed as dark matter dominated as we believe, and yet they can form rings through gentle processes, it implies that dark matter halos can have a much more complex and varied structure than a simple, smooth sphere. Alternatively, if future observations rule out gentle formation methods, it could mean that some UDGs are not the dark matter-rich behemoths we think they are. Perhaps they are failed galaxies that lost most of their dark matter early on, making them more susceptible to having their visible material shaped into a ring by a past encounter. Each ringed ultra-diffuse galaxy is therefore a crucial natural experiment, testing the limits of our theories about galaxy formation and the fundamental properties of dark matter. These faint, enigmatic rings challenge us to find new pathways of galactic evolution, pathways that operate not with a bang, but with the most delicate and patient of whispers. Just when you think a single, perfect ring is the ultimate expression of cosmic structure, the universe unveils a galaxy that resembles a celestial bullseye. We move from the simple elegance of Hoag's object to the breathtaking complexity of systems like AM0647-741, where you don't find just one ring, but multiple concentric rings nested within one another like the growth rings of a gargantuan tree. This is the phenomenon of rings within rings, a layered architecture that suggests a history far more complex than a single defining collision. The most intuitive explanation for this intricate structure is a sequence of violent events. Imagine a galaxy still recovering from the shockwave of one collision that carved out its first brilliant ring. Then, millions of years later, another smaller galaxy ventures too close, perhaps on a slightly different trajectory, and plunges through the center once more. This second impact sends a new density wave rippling outward. But this new wave doesn't simply replace the first. It propagates through a galaxy that has already been fundamentally altered. The existing ring, now populated with stars and cleared of gas, might act as a boundary, forcing the new wave to form a second ring either inside or outside the original. In this scenario, each ring is a fossilized timestamp of a separate galactic trauma, a celestial archive of violence. Computer simulations of such sequential collisions show that under the right conditions, these multiple waves can indeed create stable, concentric rings, painting a picture of a galaxy that has endured a tumultuous history of repeated encounters. However, the cosmos often prefers elegance over brute force, and an alternative theory suggests such complexity can arise from within, without the need for multiple cataclysms. This involves the fascinating concept of resonance. Just as a skilled musician can create a sustained note by blowing air at just the right frequency to resonate within a flute, gravitational forces can set up resonances within a galaxy. The central core, with its specific mass and rotation, creates a predictable gravitational field. Certain distances from the center become resonant radii, where the orbital period of gas and stars syncs up harmoniously with the overall dynamics of the galaxy. Gas clouds orbiting at these special distances experience a cumulative push each time they complete an orbit, causing them to pile up. Over time, these resonances can funnel gas into not one, but several narrow rings at different radii. A strong central bar structure can be particularly effective at driving these resonances, potentially creating a series of rings without a single external trigger. This turns the galaxy into a self-regulating instrument, its own internal music giving rise to a layered beauty. Distinguishing between these origins, a history of multiple impacts versus a single event amplified by resonance, is a major challenge for astronomers. The key lies in the details of the rings themselves. If the rings are the result of separate collisions, they might show significant age differences. The outermost ring could be the youngest, with the inner rings being progressively older relics. We would expect to see variations in the color and stellar populations, with one ring dominated by young blue stars and another by older, yellower stars. If, however, the rings are formed by resonance, they could be nearly the same age, all triggered simultaneously by the same galactic event or instability. Their stellar populations might be very similar, and their spacing would likely follow a precise mathematical ratio dictated by the galaxy's rotation curve. The existence of these multi-ringed galaxies pushes our simulations to their limits, creating a realistic model that can accurately reproduce the spacing, stability, and stellar content of concentric rings requires incredibly detailed physics, accounting for the behavior of dark matter, the hydrodynamics of gas clouds, and the feedback from supernova explosions. When a simulation successfully matches a real-world example, it's a triumph of modern computational astrophysics, giving us confidence that we are beginning to understand the complex symphony of forces that can sculpt a galaxy over billions of years. These celestial bullseyes are more than just pretty pictures. They are intricate puzzles that challenge us to decode a galaxy's entire life story, written in the luminous circles of starlight that grace the cosmic dark. Moving from the serene geometry of concentric rings, we encounter a phenomenon that injects a palpable sense of dynamical chaos into the picture. In a perfectly orderly universe, you might expect a ring galaxy to spin with the serene predictability of a carousel, the outer ring and the central core rotating together as a single, unified system. But the cosmos delights in disorder. Astronomers have discovered ring galaxies where this basic harmony is broken, where the ring is spinning at a sharp, tilted angle, completely misaligned with the rotation of the central galaxy. It's as if the outer wheel of a car was turning sideways while the axle remained straight, a configuration that seems to defy the very principles of rotational stability. This kinematic misalignment is not a minor curiosity. It is a profound dynamical puzzle that challenges our understanding of how gravitational systems evolve over cosmic time. To grasp why this is so strange, consider how a typical disk galaxy forms. It coalesces from a vast, slowly rotating cloud of gas that collapses, conserving its angular momentum. This process naturally produces a flat structure where everything spins around a single, common axis, like a well-tossed pizza dough spinning in the air. The entire system finds its lowest energy state by aligning this way. So, finding a mature galaxy where the core and the ring are spinning on different planes suggests something dramatic has happened to throw this natural order into disarray. The most likely culprit, once again, is a galactic collision, but with a critical twist. In this scenario, the smaller intruder galaxy did not make a clean, head-on pass through the center. Instead, it approached at a steep, oblique angle, delivering a gravitational kick that was off-center. This glancing blow would have imparted a significant amount of angular momentum in a direction that did not match the original spin of the larger galaxy. The ring of stars that forms from the resulting shockwave would therefore inherit this new, tilted rotational axis, leaving the original core spinning on its original, now misaligned path. The true mystery, however, is not how the misalignment began, but how it has managed to survive. According to our understanding of gravity, such a configuration should be highly unstable. The central galaxy is not just a point mass, it is embedded within an extensive halo of dark matter. The misaligned ring orbiting within this halo should experience a relentless effect known as dynamical friction. As the ring moves, it gravitationally tugs on the dark matter particles in the halo, creating a slight wake behind it. This wake, in turn, exerts a gravitational drag on the ring, slowly but surely sapping its energy and causing its orbit to decay and its tilt to diminish. The expectation is that, over a few 100 million years, a relatively short time on a cosmic scale, this friction should force the ring to settle into the same plane as the central galaxy's equator. The fact that we observe strongly misaligned rings tells us that either the collision that created them was extremely recent, which seems statistically unlikely for the number we see, or something is fundamentally wrong with our calculations about how quickly dynamical friction should work. This persistence of misalignment forces astronomers to consider more exotic possibilities. One idea is that the dark matter halo itself is not the simple, spherical distribution we often assume. If the halo is significantly flattened or triaxial, shaped more like a football than a basketball, its gravitational field could contain stable orbits that are permanently tilted. The ring could be locked in to one of these orbits, preventing the damping effect of dynamical friction from bringing it into alignment. Another, more radical concept revisits the nature of dark matter. If dark matter particles can interact with each other, creating a form of internal friction within the halo itself, this could alter how the halo responds to the misaligned ring, potentially reducing the overall drag and allowing the tilted configuration to persist for much longer periods. Each misaligned ring we discover acts as a natural experiment, testing these sophisticated theories about the hidden architecture of galaxies. Studying these cosmic wobbles provides a unique clock for dating galactic collisions. By measuring the precise degree of misalignment and combining it with sophisticated simulations that model the effects of dynamical friction, astronomers can estimate how long ago the triggering impact occurred. A ring that is only slightly tilted might be an older system well on its way to settling down. A ring that is spinning almost perpendicularly, however, signals a very recent and violent encounter. This turns kinematic misalignment from a mere curiosity into a vital diagnostic tool, allowing us to construct a timeline of galactic interactions and understand the frequency of these transformative events throughout the history of the universe. The tilted ring is a lasting signature of a past violence, a dynamical fossil that records the angle and force of an impact that happened billions of years ago, preserving a moment of cosmic chaos in the slow, grinding mechanics of gravity. But what if these beautiful cosmic rings could serve a purpose beyond just baffling astronomers? What if they could become tools, literal yardsticks for measuring the vast expanses of the cosmos? This brings us to a concept that has long been a cornerstone of observational cosmology: the search for reliable standard candles. A standard candle is any astronomical object that has a known intrinsic brightness. If you know how bright something truly is, and you measure how dim it appears from Earth, you can calculate its distance with remarkable precision. For decades, astronomers have used specific types of stars like Cepheid variables and certain kinds of supernova explosions as these cosmic measuring tapes. The problem is, even the brightest stars can only be seen so far. To probe the deepest reaches of the universe and understand its large-scale structure and expansion history, we need standard candles that are incredibly luminous and, crucially, very uniform in their nature. This is where ring galaxies present a fascinating, though highly challenging, possibility. The allure is immediately obvious. Imagine a class of ring galaxies formed by a very specific type of collision, one so similar in its mechanics that it always produces a ring of nearly identical physical size and luminosity. If such a class exists, then every time we spot one of these galaxies anywhere in the universe, we would know its true diameter and its true brightness. By measuring its apparent size and dimness in our telescopes, we could calculate its distance with a single observation, no matter how far away it is. The theoretical appeal is immense. A ring galaxy is vastly brighter than a single star, making it visible across billions of light years. Furthermore, if the ring formation process is a standardizable event, it could provide a brand new rung on the cosmic distance ladder, potentially offering an independent check on measurements made with supernova or other methods. However, the path to turning this idea into a practical tool is fraught with immense difficulties. The primary challenge is the very thing that makes ring galaxies so interesting: their individuality. Is any galactic collision truly identical to another? The outcome of a ring-forming impact depends on a delicate dance of variables: the size and mass of the two galaxies involved, their relative speed, the angle of collision, and even the amount of gas each one contained. A slight difference in any of these parameters could result in a ring that is larger, smaller, brighter, or fainter than another. Calibrating ring galaxies as standard candles would require us to find a subset that have all experienced such a similar trauma that their rings are virtually interchangeable. Astronomers would need to identify a specific fingerprint, a unique combination of the ring's color, the brightness ratio between the ring and the core, and the ring's expansion velocity that signals a truly standardized object. Current research is focused on tackling this calibration problem head-on. The strategy involves finding a sample of ring galaxies that are close enough for us to measure their distances using other, more established methods, like Cepheid variables within them. By carefully studying these nearby rings, we can attempt to correlate their observable properties with their known intrinsic brightness. Do all rings with a specific width and a certain spectral signature have the same luminosity? If a clear pattern emerges from the local sample, we could then apply that relationship to distant, faint rings whose distances are unknown, using them as standard candles to map the far universe. This is a painstaking process requiring exquisitely detailed observations from telescopes like Hubble and James Webb to dissect the stellar populations and dynamics of each candidate ring. The potential payoff, however, makes the effort worthwhile. If successfully calibrated, ring galaxies could offer a unique advantage. Unlike a supernova, which blazes brilliantly for only a few weeks before fading, a ring galaxy is a persistent object. We can observe it repeatedly, refining our measurements over time. Moreover, because a ring is an entire galaxy, it contains a wealth of ancillary data within it, the motion of its stars, the age of its populations, that can be used to cross-check the standard candle assumption. A reliable ring galaxy standard candle would provide a powerful, independent probe of the Hubble constant, the rate of the universe's expansion, and could help resolve the current tension between different measurement techniques. While they are not yet a tool we can reliably use, ring galaxies represent a promising and audacious frontier in cosmology, where the chaotic beauty of a galactic wreck might one day help us chart the grandest scales of reality. This search for the progenitor is a cosmic detective story, and our primary tool for cracking the case is the supercomputer. Astronomers don't just guess, they run incredibly sophisticated simulations, essentially creating virtual universes inside powerful machines. They start with the ring galaxy we see today. Its size, the mass of its ring and core, the speed at which the ring is expanding, and then they work backward. They program in the known laws of physics, gravity, hydrodynamics, the behavior of gas and stars under extreme stress, and then they ask the computer to rewind the tape. They try countless scenarios. What if the intruder galaxy was large and gas-rich? What if it was small and dense? What if the collision was perfectly head-on or at a slight angle? By running these simulations forward and comparing the end result to the actual, observed ring galaxy, they can identify which initial conditions produce a near-perfect match. It's a process of elimination on a galactic scale. The characteristics of the intruder galaxy are slowly coming into focus through this painstaking work. The evidence points strongly toward it being a smaller galaxy, often referred to as a dwarf galaxy. A larger, equal-mass collision would likely have resulted in a much more chaotic mess, completely destroying the disk structure of the larger galaxy rather than carving out a neat ring. The intruder also needed to be gas-rich. If it were a barren collection of old stars, its passage would have caused a gravitational disturbance, but it wouldn't have provided the extra fuel that often gets incorporated into the brilliant ring of new stars we observe. This gas acts as the kindling for the stellar firestorm, and its presence in the intruder is a crucial clue, but perhaps the most critical piece of evidence is what's missing. In many cases, the smaller galaxy is nowhere to be found in the vicinity of the ring. This suggests that the collision was what astronomers call a high-speed encounter. The intruder galaxy wasn't captured. It was like a bullet passing through a target, moving so fast that after the impact, it continued on its way, escaping the gravitational pull of the larger galaxy it had just transformed. It's now a ghost, lost to the vastness of intergalactic space, its only legacy being the beautiful, wounded ring it left behind. In other cases, like with the Cartwheel Galaxy, a potential culprit can be identified. Smaller companion galaxies are often found nearby, which could be the remnants of the intruder, now stripped of their gas and orbiting their massive, ringed creation. This forensic analysis allows us to paint a surprisingly detailed picture of the galaxy that existed before the cataclysm. The progenitor was likely a normal, relatively flat disk galaxy, quite possibly a spiral similar to our own Milky Way or the Andromeda Galaxy. It had a rotating disk of stars, gas, and dust, and probably a central bulge. It was a functioning, star-forming system, evolving quietly on its own. The collision that created the ring was not a meeting of two bizarre objects. It was a random act of violence inflicted upon a perfectly ordinary galaxy, transforming it into the extraordinary celestial oddity we study today. This realization is humbling. It tells us that any galaxy, even our own, could one day undergo a similar transformation if another galaxy happens to cross its path at just the right or just the wrong angle. But the universe has a way of taking our neatly defined categories and blurring their edges in the most spectacular fashion. We've been discussing rings that form around spiral or disk galaxies, but what happens when we find a ring encircling a galaxy that, by all rights, shouldn't have one at all? This brings us to the deeply counterintuitive case of rings around elliptical galaxies. Imagine a celestial object that looks like a fuzzy, golden egg, a smooth, nearly featureless collection of ancient stars orbiting in random directions, the result of billions of years of galactic mergers that have erased any trace of a disk. This is a classic elliptical galaxy, the quiet retirement home for stellar populations. Now, imagine that this serene object is suddenly girded by a perfect, thin ring of brilliant blue stars. It's a combination that seems to defy logic, a cosmic oxymoron that challenges the very story we tell about how galaxies live and die. The peculiarity of this pairing lies in the fundamental nature of elliptical galaxies themselves. Unlike the orderly, rotating disks of spiral galaxies, ellipticals are thought to form through a process of violent hierarchical merging. When two spiral galaxies of roughly equal size collide, their delicate disk structures are utterly destroyed. The gravitational chaos of the merger randomizes the orbits of billions of stars, puffing the new galaxy up into a three-dimensional football-shaped swarm. Any neat, rotating rings of gas would be shredded and assimilated in this cosmic blender. This is why the standard model of elliptical galaxy formation is fundamentally at odds with the presence of a pristine, rotating ring. The very event that creates the elliptical should, in theory, destroy any such delicate structure. Finding a ring around an elliptical is like finding a perfectly preserved, delicate soap bubble floating unscathed inside a factory that manufactures wrecking balls. So how does such an impossible structure come to be? Astronomers are investigating several fascinating scenarios, each a testament to the dynamic and creative violence of the cosmos. One leading theory involves a specific type of galactic cannibalism. Imagine a large elliptical galaxy, the product of ancient mergers drifting through space. A small, gas-rich dwarf galaxy, perhaps a tiny spiral, ventures too close. The immense gravitational tide of the elliptical galaxy tears the dwarf apart. But instead of being completely consumed, the dwarf stars and gas are stretched into a long stream that gradually settles into a stable circular orbit around the giant elliptical. Over time, the gas in this stream collapses to form new stars, igniting a brilliant ring around the otherwise dead galaxy. In this scenario, the ring is not a survivor of the elliptical's formation. It is a much later addition, a cosmic garnish acquired long after the galaxy's main course of mergers was finished. Another compelling idea flips the script entirely, suggesting that some of these ringed ellipticals might not be true ellipticals at all. They could be lenticular galaxies which possess a central bulge of old stars like an elliptical, but also a faint remnant disk of stars and dust. If this disk is very faint, the galaxy might be misclassified as an elliptical. A collision could then trigger a density wave within this faint disk, creating a ring of star formation that makes the underlying disk visible. The galaxy would then be a ringed lenticular, not a ringed elliptical, resolving the contradiction. Distinguishing between these possibilities requires ultra-deep observations to detect the faintest whispers of a disk that might have been missed in earlier surveys. The implications of confirming a genuine ring around a bona fide elliptical galaxy are profound. It would force a significant revision of our understanding of galactic evolution and the stability of galactic structures. It suggests that under very precise conditions, a delicate ring can form and persist within the gravitational field of a galaxy whose internal dynamics are characterized by random, chaotic motions rather than orderly rotation. This would point to a remarkable resilience in these structures and a greater complexity in the interaction process than our models currently account for. Each ringed elliptical serves as a critical edge case, testing the limits of our theories and reminding us that the universe always has another surprise in store, often hidden in plain sight around the seemingly simplest of objects. We have explored the immense gravitational forces that sculpt these cosmic rings, but there is another invisible power at work, one that is far more difficult to measure yet could be just as crucial to the ring's destiny. Beyond the pull of gravity and the shock of collision, the universe is threaded with vast, invisible magnetic fields. Within a ring galaxy, these fields are not passive spectators. They are active players, woven into the fabric of the gas and dust, and their role in the galaxy's dramatic rebirth is one of the most complex and elusive puzzles astronomers are trying to solve today. The story of these magnetic fields begins with the progenitor galaxy. Like our own Milky Way, a typical spiral possesses a large-scale magnetic field, incredibly weak by earthly standards but sprawling across tens of thousands of light-years. This field is thought to be generated and sustained by a dynamo effect, driven by the rotation of the galaxy's disk and the turbulent motions of its ionized gas. It's a delicate, organized structure. Then the collision happens. The cataclysmic impact that sends a density wave racing outward does not just compress gas. It violently churns and stretches the entire magnetic field of the galaxy. Think of it like pulling on a tangled ball of magnetic field lines. The act of stretching them can dramatically amplify their strength, intensifying the magnetic forces at play within the collapsing gas clouds. This amplification could have a profound effect on the very heart of the star formation process. As the density wave compresses the interstellar gas to trigger the birth of new stars, the magnetic field is caught in the crush. Magnetic fields exert a pressure of their own, a resistance to being squeezed. In some cases, this magnetic pressure might act as a support mechanism, propping up a cloud against its own gravity and actually slowing down the collapse into stars. In other scenarios, the amplified field might channel and guide the flow of gas, funneling material along specific magnetic field lines into dense knots where collapse becomes inevitable. The critical question is whether the magnetic field in a ring galaxy acts as a brake on star formation or as an accelerator, and the answer likely depends on the specific conditions left in the wake of the collision. Observing these magnetic fields directly is a monumental challenge. Astronomers cannot see them. They must detect them indirectly by studying the light that passes through the galaxy. A phenomenon known as Faraday rotation is a key tool. As polarized radio waves from a distant quasar or a pulsar travel through the magnetized plasma of the ring galaxy, the magnetic field causes the direction of the radio waves to slowly rotate. By meticulously measuring this rotation, scientists can map the strength and direction of the hidden magnetic field threading the ring. Early results from such studies suggest that the magnetic fields in some rings are indeed highly ordered and surprisingly strong, potentially even stronger than those found in undisturbed spiral galaxies, lending support to the idea that the collision has amplified them. The influence of these fields may extend to the ring's very stability and longevity. The magnetic field lines woven through the gas could act like a cosmic skeleton, providing a supporting structure that helps the ring maintain its coherent shape against the tidal forces that would otherwise tear it apart. Furthermore, as massive stars in the ring explode as supernova, they inject tremendous energy back into their surroundings. Magnetic fields can help channel this feedback, shaping the expanding supernova remnants and determining how efficiently this energy is dispersed, which in turn regulates whether star formation in the ring continues in a sustained burst or is quickly shut down. The magnetic field, therefore, is not just a detail. It is an integral part of the ring galaxy's ecosystem, a fundamental force intertwined with gravity and radiation in determining whether this beautiful structure is a fleeting flash in the pan or a long-lasting phase of galactic evolution. Unraveling its precise role is essential to moving from a simple picture of what a ring galaxy looks like to a complete understanding of how it truly lives and dies. Amid the fiery chaos of a ring galaxy's star-forming frenzy, something even more remarkable can occur. The immense density wave that triggers the birth of millions of stars doesn't just create a uniform band of light, it can also spawn distinct, concentrated knots of material. Within the ring, vast clouds of gas and dust compressed by the shockwave can themselves collapse under their own gravity. But sometimes these collapsing regions are so massive and contain so much material that they don't just form individual stars. They can begin to form an entire gravitational system of their own. These are not mere star clusters, they are potential new galaxies in the process of being born right out of the wreckage of the old. Astronomers call these infant systems tidal dwarf galaxies, and their existence blurs the line between destruction and creation in the cosmos. The formation process is a fascinating byproduct of the galactic collision. As the intruder galaxy plows through the larger disk, it doesn't just push gas outward in a smooth wave, it also violently shreds and stretches the existing structure. Long tidal tails of gas, dust, and stars are pulled out from both galaxies. Within these tails, and particularly within the dense, shocked environment of the newly formed ring, regions of gas can become so dense that their self-gravity overcomes the tidal forces trying to pull them apart. Imagine a stream of water breaking up into individual droplets. On a cosmic scale, a stream of galactic material can fragment into these collapsing clumps. If a clump contains enough mass, typically billions of times the mass of our Sun, it can become gravitationally bound, starting its own independent life as a dwarf galaxy. This leads to one of the most heated debates in modern astronomy. Do these tidal dwarf galaxies contain dark matter? According to the standard model of galaxy formation, dark matter is the essential ingredient. Vast halos of this invisible substance are thought to have collapsed first in the early universe, providing the gravitational scaffolding necessary for normal baryonic matter, the stuff of stars, planets, and us, to clump together and form galaxies. Every galaxy we know, from the largest spiral to the smallest dwarf, is believed to be nestled within and dominated by a dark matter halo. But tidal dwarf galaxies present a direct challenge to this fundamental rule. They are not formed from the top-down collapse of a dark matter halo. They are assembled from the bottom up from gas and stars that were already within a galaxy. This gas was itself already within the dark matter halo of the progenitor galaxy. When it was ejected to form the tidal dwarf, did the dark matter come with it? Most theoretical models suggest the answer is no. Dark matter, as we understand it, is collisionless. The particles that make up the dark matter halo pass through each other and through normal matter without interacting except through gravity. During a galactic collision, the dark matter halos of the two galaxies are thought to largely pass through each other, their distribution smoothed out but not drastically altered on small scales. The visible gas, on the other hand, is collisional. Gas clouds slam into each other, heat up, and get compressed. This difference in behavior means that when tidal forces pull a stream of gas out of a galaxy to form a tidal dwarf, the dark matter halo, being more diffuse and spread out, likely does not get pulled out with the same efficiency. The resulting tidal dwarf galaxy would therefore be made almost entirely of baryonic matter, the stars and gas we can see. It would be a galaxy born without a dark matter skeleton, a seemingly impossible object according to our standard theories. The hunt for observational evidence is crucial to resolving this debate. Astronomers studied tidal dwarf candidates by measuring their mass in two ways. First, they calculate the baryonic mass by adding up the light from all the stars and estimating the mass of the detected gas. Then, they measure the total gravitational mass by observing how fast the stars and gas are orbiting within the dwarf galaxy. In a conventional galaxy, the total mass inferred from the orbital speeds is far greater than the visible mass, revealing the presence of dark matter. For a true tidal dwarf galaxy, the prediction is that these two masses should be nearly equal. If the orbital speed is what you would expect from the visible mass alone, it would be powerful evidence that the object is indeed a dark matter-free zone. Some studies of tidal dwarfs near colliding galaxies have shown exactly this, supporting the pure baryonic picture. However, other observations have been more ambiguous, suggesting there might be more mass present than can be accounted for by visible matter, reigniting the debate. The implications of confirming a population of dark matter-free galaxies would be profound. It would validate our understanding of how dark matter behaves in collisions, showing that it truly is collisionless and remains in a large halo while the messy, collisional gas is what gets flung out to form new structures. This would provide a crucial test for the cold dark matter model. Furthermore, studying these pure baryonic galaxies would offer a unique laboratory. They would allow us to observe how galaxies form and evolve under the influence of gravity alone, without the dominant smoothing effect of a dark matter halo. Would they be more fragile? Would their internal dynamics be drastically different? Each tidal dwarf galaxy orbiting within a ring is therefore more than just a celestial curiosity. It is a natural experiment that could help us refine our most fundamental theories about the invisible component that shapes our universe. Now we turn our attention to a more subtle, yet equally revealing, aspect of these cosmic rings, their chemical fingerprint. Every star is a cosmic chemist, forging heavier elements in its core, and if it's massive enough, scattering them across space in a supernova explosion. These elements, which astronomers collectively call metals, become the building blocks for subsequent generations of stars and planets. By analyzing the light from stars, we can measure their metallicity essentially, the percentage of their composition that is made up of elements heavier than hydrogen and helium. And when we perform this analysis on a ring galaxy, comparing the stars in the brilliant blue ring to those in the quiet golden core, we uncover a dramatic story of the galaxy's violent history and its aftermath. The primary tool for this cosmic chemistry is spectroscopy. When starlight passes through a spectrograph, it is spread out into a rainbow of colors known as a spectrum. Imprinted on this rainbow are dark lines, like a unique barcode for each star. These absorption lines are created when specific elements in the star's outer atmosphere absorb light at very precise wavelengths. The strength and breadth of these lines tell astronomers not only which elements are present but also in what abundance. By carefully studying the patterns for elements like iron, oxygen, and silicon, scientists can calculate the metallicity of the stellar population. It's a painstaking process, but it allows us to read the chemical autobiography of a galaxy written in the light of its stars. In a standard, undisturbed spiral galaxy like our Milky Way, we expect to find a clear metallicity gradient. The central regions, having undergone many more cycles of star formation and supernova enrichment over billions of years, are expected to be metal-rich. As you move outward toward the galactic suburbs, the metallicity generally decreases because those regions have experienced less star formation and have been less polluted by the products of previous stellar generations. This gradient is a natural consequence of a galaxy evolving quietly and gradually from the inside out. But a ring galaxy shatters this expectation. The chemical picture it presents is often bizarre and inverted. The stars in the central core, which are ancient relics of the progenitor galaxy, typically show a metallicity you would expect for an old population moderately high, reflecting a long history of enrichment. The real surprise lies in the ring. One might assume that this ring, being made of brand new stars formed from gas that was pushed outward from the inner galaxy, would have a high metallicity as well. After all, that gas should have been enriched by the same previous generations of stars that enriched the core. Sometimes this is the case, pointing to a thorough mixing of the galaxy's gas reservoir during the collision. The intruder galaxy's passage acts like a giant spoon, stirring the galactic pot and ensuring the gas that forms the ring is well mixed and chemically uniform. However, astronomers have also discovered ring galaxies where the metallicity in the ring is surprisingly low, much lower than in the core. This is a profound clue. It suggests that the gas which collapsed to form the brilliant blue ring did not come predominantly from the metal-rich inner regions of the progenitor galaxy. Instead, a significant portion of it must have been pristine, metal-poor gas that was donated by the intruder galaxy itself. If the colliding galaxy was a gas-rich dwarf, a type of galaxy known for its low metallicity, its contribution of fresh, unenriched hydrogen and helium could have diluted the metal content of the ring. In this scenario, the ring is a hybrid structure built from a mixture of stirred-up gas from the main galaxy and virgin gas from the intruder, its metallicity acting as a direct measure of that mixture's ratio. This chemical evidence can even reveal the dynamics of the collision itself. If the ring shows a uniform metallicity all the way around its circumference, it suggests the gas was thoroughly mixed during the event, perhaps by turbulent processes as the shockwave propagated outward. But if there are patches of the ring with higher or lower metallicity, it could indicate that the mixing was incomplete. These chemical patches might be fingerprints of specific clouds of gas that originated in different parts of the progenitor or intruder galaxy, preserving their individual identities within the larger ring structure. By mapping these subtle variations, astronomers can essentially trace the flow of material during the impact, understanding not just that a collision happened, but how it unfolded on a detailed chemical level. The metallicity of a ring galaxy is therefore far more than a number. It is a detailed logbook of the materials involved in its creation and a chronicle of the violent mixing process that gave it birth. Among the countless ring galaxies catalogued by astronomers, one stands apart as the quintessential example of cosmic perfection, an object so iconic that it has become the benchmark against which all others are measured. This is Hoag's object, a galaxy that looks less like a natural formation and more like a meticulously crafted piece of celestial art. Discovered by astronomer Art Hoag in 1950, it presents a spectacle that is both breathtaking and deeply puzzling. A perfectly round, golden yellow core of ancient stars is encircled by a flawless, brilliant blue ring of youthful stars, with a dark, seemingly empty gap of profound emptiness separating the two. It is this stark, clean separation that elevates Hoag's object from a mere curiosity to a long-standing enigma in extragalactic astronomy. The mystery of Hoag's object begins with its almost artificial symmetry. Unlike the Cartwheel Galaxy with its faint spokes and complex inner ring, Hoag's object presents a simplicity that is unnerving. The core is not a puffed-up bulge, but a smooth, concentrated sphere of stars resembling a small elliptical galaxy. The ring is a pristine circle with no visible connection to the core, appearing to float serenely around it. The gap between them is not just dark, it is remarkably devoid of any obvious stars, dust lanes, or gas clouds that would indicate a bridge of material. This clean detachment is the central puzzle. If a galactic collision created this ring, as is the leading theory for most ring galaxies, where is the evidence of the disruption? One would expect to see tidal streams, faint arcs of stars, or some kind of structural debris linking the ring to the core, the telltale scars of a violent past. Yet Hoag's object shows none of this. It appears pristine, untouched, and perfectly formed, as if it has always existed in this state. This lack of obvious debris has fueled alternative theories about its origin. Perhaps Hoag's object is not the product of a collision at all, but the result of an extreme form of internal instability. Some models suggest that billions of years ago, the progenitor galaxy may have possessed a massive, unstable bar of stars and gas at its center. Over time, instabilities in this bar could have funneled an enormous amount of gas outward to a specific resonance radius, where it accumulated and ignited into a ring of star formation. The bar itself would then have dissolved, leaving behind the central core and the isolated ring. This secular evolution scenario would be a slow, graceful process, avoiding the violent chaos of a collision and potentially explaining the object's clean appearance. However, this theory also faces challenges, as it requires a very specific and delicate set of conditions to produce such a perfect, symmetric ring without any residual structure. Compounding the mystery is the sheer scale of the gap. The distance between the inner edge of the blue ring and the outer edge of the yellow core is immense, spanning tens of thousands of light years. For comparison, that gap is wider than the entire diameter of many dwarf galaxies. What physical process could so effectively clear out such a vast volume of space, leaving it a stellar desert? A collision might push gas outward, but it would likely leave behind a population of older stars from the original disk, which would appear as a faint, diffuse light in the gap. Deep observations with telescopes like the Hubble Space Telescope have searched for this faint starlight, and while some very faint red giant stars have been detected, their numbers are far fewer than what most collision models would predict. This sparse population only deepens the puzzle, suggesting that the progenitor galaxy's disk was either unusually thin or that the ring-forming event was exceptionally efficient at sweeping the region clean. The enduring allure of Hoag's object lies in its role as a cosmic control experiment. Its perfection makes it a unique test case for our theories, because it lacks the complicating factors seen in other ring galaxies like inner rings, spokes, or obvious companion galaxies. Astronomers can focus on the most fundamental physics of ring formation. It presents a pure, idealized geometry against which computer simulations can be rigorously judged. A successful model must not only create a ring, but must also explain the vast, empty gap and the pristine condition of the central core. Every new observation, from detailed measurements of the ring's expansion velocity to ultra-deep searches for faint streams of stars, provides another constraint, helping to eliminate some theories and refine others. Hoag's object remains a classic unsolved mystery, not because we have no ideas, but because it so elegantly defies a simple, single explanation, reminding us that the universe is capable of a serenity and order that can, paradoxically, be more baffling than its most violent chaos. Within the brilliant blue fires of a ring galaxy's star-forming front, astronomers are offered a unique opportunity to witness the most dramatic and fleeting events in the universe, cosmic transients. These are the sudden, brilliant flashes that appear without warning and then fade away: supernova, gamma-ray bursts, and other stellar cataclysms. While these events can happen anywhere, their occurrence within the well-defined environment of a ring galaxy transforms them from isolated fireworks into precise scientific instruments. The key lies in the ring itself acting as a cosmic calendar, because we understand that the entire ring of stars was born in a single, recent burst triggered by the collision. We know with remarkable accuracy the age of every massive star within it. This knowledge turns the ring into a controlled laboratory for stellar evolution, allowing us to connect the dots between a star's birth, its short life, and its violent death in a way that is impossible in a more mixed-age environment like our own galaxy. Consider a supernova, the titanic explosion that marks the end of a massive star's life. In a typical galaxy, when a supernova flashes into view, astronomers scramble to identify the progenitor star in archived images. This is often a difficult task. The stellar population is a messy mix of ages, and the exact identity of the star that exploded can be ambiguous. But in a ring galaxy, the process is dramatically simplified. Since all the massive stars in the ring are the same age, born from the same wave of star formation, their life expectancies are governed by a straightforward rule: the more massive the star, the shorter its life. A star 100 times the mass of our Sun might live for only 3 million years, while a star 20 times the Sun's mass could last 10 million years. Therefore, when a supernova occurs in the ring, its very location provides an immediate clue about the mass of the star that created it. A supernova that goes off just a few million years after the ring formed must have come from an extremely massive, short-lived progenitor. A supernova that occurs 10 million years later likely came from a slightly less massive star. This allows astronomers to directly test and refine their models of stellar evolution, confirming predictions about which types of stars produce which kinds of supernova. The potential for discovery extends to the most powerful explosions in the cosmos, gamma-ray bursts. These are brief, intense flashes of high-energy radiation, believed to be associated with the death of the most massive stars or the mergers of exotic compact objects like neutron stars. The star-forming rings of these galaxies are ideal hunting grounds for such events, as they are factories for producing the very types of stars that lead to these spectacular ends. If a gamma-ray burst were detected originating from a ring galaxy, the known age of the stellar population would be an invaluable piece of the puzzle. It would immediately tell us the lifespan of the progenitor system, tightly constraining the models that attempt to explain how these incredible blasts are launched. Did it come from a rapidly rotating, ultra-massive star collapsing directly into a black hole? The age of the ring would help us determine the minimum mass required for such a cataclysm. This timed environment also opens a window into the chemical enrichment of the galaxy in near real time. The first supernova to explode in the ring will be from the most massive stars. These explosions seed the surrounding ring with heavy elements like oxygen, neon, and magnesium. Later supernova from progressively less massive stars will contribute different elements such as iron. By observing the sequence of these explosions and analyzing the elemental signatures in the light of each event and in the surrounding gas, astronomers can watch the ring's chemical composition evolve. It's like watching a live demonstration of how generations of stars have built up the periodic table of elements that make up our world. This transforms the ring from a static picture into a dynamic movie, where each transient event is a frame that advances our understanding of how galaxies manufacture the raw materials for planets and life. Looking billions of years into the future, the brilliant spectacle of a ring galaxy is destined to fade, its structure unraveling through the relentless pull of gravity and the explosive feedback of its own stars. The very processes that gave it birth also contain the seeds of its eventual transformation. The most immediate force of change comes from within the ring itself, from the massive, luminous stars that define its brilliant blue color. These stellar behemoths live fast and die young, and after only a few tens of millions of years, they will begin to end their lives in a spectacular series of supernova explosions. Each detonation is more than just a stellar death. It is a powerful regulatory event. The blast waves from these supernova will rip through the surrounding interstellar gas, heating it to immense temperatures and driving it out of the ring. This process, known as feedback, effectively blows away the raw fuel required for future star formation. The ring's brilliant blue hue, a signature of youth, will gradually dim as the last of the massive stars explode, leaving behind a population of longer-lived, smaller, and cooler stars that will cause the ring to shift in color from blue to yellow and eventually to a dull red. Meanwhile, the delicate gravitational dance that maintains the ring's structure is also under threat. The initial density wave that triggered the ring's formation will continue to propagate outward, but it will eventually weaken and lose its coherence. As it does, the organized compression that sustains the ring's sharp profile will diminish. At the same time, the ring itself is not a perfectly stable structure. Gravitational instabilities will begin to fragment it. Small overdense regions within the ring will start to exert a stronger pull on their surroundings, causing the ring to break up into distinct clumps and arcs of stars. Sophisticated computer simulations show this process clearly. What begins as a perfect circle slowly develops kinks and knots, eventually resembling a string of luminous pearls before the string itself snaps, scattering the stellar clusters into a more disordered configuration. The iconic ring shape, so defined and striking, will slowly blur and dissolve into a more amorphous cloud of stars orbiting the galactic center. The ultimate fate of the system is shaped by the complex interplay between the fading ring and the central core. One possibility, revealed by dynamical models, is that the ring will simply dissipate, as its stars are scattered by internal instabilities and its gas is depleted by star formation and supernova winds. The ring will expand and fade into the surrounding halo, leaving behind a galaxy that may resemble a peculiar, diffuse elliptical galaxy or a large spheroidal system. The central core, already ancient, will remain, now surrounded by a faint, extended glow of stars that were once part of the brilliant ring. Another, more dynamic fate involves the ring falling inward. If the galaxy possesses a significant amount of dark matter that exerts a strong gravitational drag, or if a significant amount of gas remains and can lose energy through collisions and radiation, the ring's orbit could decay. Over billions of years, the ring's material could migrate inward, funneling gas toward the core and potentially triggering a final, central burst of star formation, effectively rejuvenating the dormant center before the entire system settles into a more common elliptical form. The final galactic type that emerges from this evolution depends heavily on the initial conditions of the collision. A ring galaxy born from a relatively minor interaction might simply relax back into a distorted spiral galaxy if its disk can reform. However, the violent, head-on collisions that create the most spectacular rings are truly transformative events. Simulations consistently show that these systems are unlikely to ever return to a stable spiral structure. The damage to the original disk is too severe. Instead, they are far more likely to evolve into lenticular galaxies, which possess a central bulge and a disk but no spiral arms, or into genuinely elliptical galaxies, where all traces of orderly rotation are erased and stars move in random orbits. The ring galaxy, therefore, is not a permanent class of object but a dramatic, transient phase in the life cycle of galaxies, a brilliant but short-lived rebirth that ultimately leads to a quieter, more common retirement. Its fate illustrates a fundamental cycle of the cosmos. From the chaos of collision comes a moment of exquisite structure, which then inevitably gives way to a new, settled equilibrium. Its story written in the slow, patient unwinding of gravity over cosmic time. While the brilliant ring commands our attention with its firestorm of stellar birth, an even more powerful engine may be lurking in the shadows of the galactic core. At the heart of most large galaxies, including our own Milky Way, resides a supermassive black hole, a gravitational monster weighing millions or even billions of times the mass of our Sun. In most galaxies, this leviathan slumbers quietly, but in some, it awakens, feasting on surrounding gas and unleashing a torrent of radiation that can outshine the entire galaxy. This is an active galactic nucleus, or AN, and its relationship with the ring galaxy phenomenon is a story of cosmic cause and effect that does not follow a simple script. One might logically assume that the cataclysm which forges a ring galaxy would be the perfect recipe for awakening the central black hole. The collision violently disrupts the entire galactic disk, and theory suggests that a tremendous amount of gas should be funneled inward by the gravitational chaos, falling directly toward the waiting black hole. As this gas spirals in, it forms a superheated accretion disk, and the incredible friction and magnetic fields generate the blinding light of an AGN. In this scenario, a ring galaxy should almost always be accompanied by a brilliant, active core, a double spectacle of outer and inner violence. Yet, when we look at pristine ring galaxies like Hoag's object, we find a central black hole that is remarkably quiet. This presents a fascinating paradox. Why would a collision that is so effective at driving gas outward to form a ring simultaneously fail to feed the monster at the very center? The answer may lie in the precise geometry of the impact. A perfect head-on collision, like a bullet through the center of a target, might be too clean. The gravitational shockwave propagates radially outward, effectively pushing gas away from the core in all directions. Think of it like a single, powerful shock that clears the central region rather than filling it. The gas is scooped up and driven outward to the ring-forming front, potentially starving the black hole in the process. The very event that creates the ring might also be responsible for shutting down the central engine before it ever has a chance to ignite. The AGN might be stillborn, its fuel supply stolen by the expanding wave of star formation at the galaxy's edge. However, not all ring galaxies conform to this pattern. In systems where the collision was more complex, perhaps a glancing blow or an interaction involving multiple galaxies, the outcome can be dramatically different. In these messy encounters, the dynamics are not so symmetric. Gas clouds can be sent on chaotic, intersecting orbits, and some of these streams of material will inevitably lose energy and angular momentum, cascading down into the galactic center. This is when the supermassive black hole can truly awaken. We see evidence of this in some ring-like systems where the core shines with the intense, flickering light of an AGN, a clear sign that gas is actively raining down upon the central black hole. The ring and the AGN then become two sides of the same cataclysmic coin. One is the signature of star formation triggered in the outskirts, and the other is the signature of feasting triggered at the very heart. The presence or absence of an AGN also has profound consequences for the future evolution of the ring galaxy itself. An active galactic nucleus is not a passive consumer, it is an incredibly powerful feedback mechanism. The intense radiation and powerful jets of particles blasting out from the region around the black hole can heat the surrounding gas or blow it clean out of the galaxy. This AGN feedback can effectively quench future star formation across the entire galaxy, including in the ring. A ring galaxy with a strong AGN might therefore have a much shorter-lived stellar baby boom. The brilliant blue ring could be snuffed out prematurely, its gas supply heated and dispersed by the raging furnace at the center. This creates a cosmic race between the inner and outer engines of creation and destruction, where the black hole's feast can ultimately lead to the starvation of the entire system. The silent core of a galaxy like Hoag's object, by contrast, might allow the ring to shine on for a much longer period, a more peaceful, though no less spectacular, phase of galactic rebirth. But the beauty of a ring galaxy isn't always a smooth, uniform band of light. Sometimes the cosmos prefers a more punctuated elegance. Zoom in on the brilliant blue ring of a galaxy like the Cartwheel, and you might notice that its luminosity isn't continuous. Instead, it resolves into a series of spectacular, blazing knots, incredibly bright spots spaced at seemingly regular intervals along the circular structure. This is the string of pearls effect, where the ring looks less like a solid loop and more like a celestial necklace, with each pearl being a colossal star cluster containing millions of young, massive stars. This intricate beading isn't just a beautiful accident. It's a direct signature of the physical laws governing how star formation propagates through a galaxy-scale shockwave. The origin of this stunning pattern lies in the behavior of the density wave itself. As the gravitational shockwave from the collision expands outward through the galactic disk, it doesn't push the gas in a perfectly smooth, uniform wall. Think of it less like a solid plow and more like a ripple moving through a fluid. Instabilities are inevitable. The wave front can develop what are known as gravitational instabilities, where slight overdensities in the gas begin to exert a stronger pull on their surroundings. A tiny region that is just a little denser than its neighbors will pull in more gas, making it even denser, and this process snowballs. These instabilities cause the smooth wave to fragment, breaking up into a chain of massive, collapsing clouds precisely spaced along the ring. Each of these clouds then becomes a factory for star formation on an epic scale, igniting into the brilliant pearls we observe. This process is very similar to a phenomenon seen right here in our own solar system. The rings of Saturn are not a perfectly smooth sheet of ice. They are structured into countless concentric rings and gaps, with some regions showing distinct clumpy features. This structure is caused by gravitational resonances with Saturn's moons, which tug on the ring particles and shepherd them into specific, stable patterns. In a ring galaxy, the moon is the overall gravitational field of the galaxy itself, including the core and the dark matter halo. The propagating density wave interacts with this background field, and certain radii become preferred locations for collapse, leading to the regular spacing of the star-forming pearls. It's a universal principle of physics, playing out on a scale billions of times larger. The spacing between these pearls is not random. It holds crucial information about the conditions within the galaxy. The distance between one pearl and the next is determined by a property called the gene's length. This is a critical threshold that dictates whether a cloud of gas will collapse under its own gravity. It depends on the gas's pressure and density. If a region is larger than the gene's length, it will collapse. If it's smaller, pressure forces will hold it up. In the high-density environment of the shockwave, the gene's length has a specific value. The instabilities in the wave front naturally fragment it into chunks that are roughly the size of this critical length, which is why the pearls appear so regularly spaced. By measuring the distance between these clusters, astronomers can essentially take the temperature and pressure of the gas in the ring, using the pearls as a cosmic barometer. Furthermore, the sheer size and brilliance of each pearl tell us about the incredible efficiency of star formation in these extreme environments. A single one of these knots can contain more stellar mass than some small dwarf galaxies. The fact that such immense structures can form simultaneously around the entire circumference of the ring indicates that the triggering mechanism, the density wave, is exceptionally powerful, creating conditions where star formation can proceed at a ferocious rate, unimpeded by the factors that normally slow it down in quieter galaxies. The string of pearls is therefore a frozen moment in a chain reaction of cosmic proportions, a direct visualization of how a single wave of pressure can ignite a galaxy-wide firestorm of creation, structured by the fundamental laws of gravity and hydrodynamics. Yet the cosmos can produce configurations even more counterintuitive than a tilted ring. We have witnessed rings that are misaligned, but what if the ring's motion was not merely tilted, but fundamentally opposed to the galaxy it encircles? Imagine a galaxy where the central core spins clockwise, while the brilliant ring of stars surrounding it rotates counterclockwise. This is not a thought experiment. It is the reality of counter-rotating rings, a phenomenon so rare it seems to defy the very logic of gravitational systems. It is the equivalent of a celestial gear spinning backwards against its main drive, a configuration that demands an extraordinarily specific and violent origin story. The profound strangeness of this motion lies in the fundamental way galaxies are born. A typical galaxy forms from the collapse of a single, massive cloud of gas that possesses a specific amount of angular momentum. As this cloud contracts, its rotation speeds up, much like an ice skater pulling in their arms, naturally forming a disk where everything spins in the same direction. This shared rotation is the galaxy's birthright, a conserved legacy from its initial conditions. For a ring to orbit in the opposite direction, it means its material must have acquired a completely different, indeed opposite, spin angular momentum from somewhere else after the main galaxy had already formed. This cannot happen through any gentle, internal process. It requires an external intervention of the most dramatic kind. The only plausible scenario that can produce such a stark contradiction involves a galactic collision, but one with a very specific set of parameters. The smaller intruder galaxy must not only approach the larger disk galaxy, but it must do so on a retrograde orbit, meaning it is moving in the opposite direction to the spin of the larger galaxy's disk. Furthermore, the encounter needs to be a direct bullseye collision or a very close pass. As the intruder plunges through, its opposite direction motion imprints that retrograde spin onto the gas and stars it tears from the larger galaxy. When this captured material settles into a ring around the core, it retains that backward motion, creating the counter-rotating structure we observe. It is a cosmic bank shot of immense precision, where the angle and spin of the incoming object are everything. The stability of such a system is a major puzzle for dynamicists. A counter-rotating ring exists in a state of constant gravitational tension with the central galaxy. The expected outcome is a rapid decay. The opposing motions should create immense friction, not in the traditional sense of physical contact, but through gravitational interactions known as dynamical friction. The retrograde ring constantly tugs against the prograde motion of the central stars and the dark matter halo, sapping its orbital energy. Most models suggest that such a ring should spiral inward and be destroyed on a relatively short timescale, perhaps within a billion years. Therefore, the mere existence of a counter-rotating ring tells us two things. First, that the collision which created it was incredibly recent in cosmic terms, and second, that our understanding of how quickly dynamical friction operates in such extreme environments may need refinement. Perhaps the dark matter halo plays a more complex role in stabilizing these seemingly impossible configurations than we currently appreciate. Observing these rare objects provides a unique laboratory for studying the physics of galactic collisions. By measuring the precise rotational speeds of the core and the ring, astronomers can work backwards to calculate the exact trajectory and velocity of the intruder galaxy. Each counter-rotating ring is a frozen record of a past impact, preserving the kinematics of the collision with exquisite detail. Furthermore, the interface between the forward spinning core and the backward spinning ring is a region of extreme shear forces where gas clouds moving in opposite directions collide. This could trigger unique and intense bursts of star formation, adding another layer of complexity to the galaxy's evolution. The counter-rotating ring is therefore more than a mere curiosity. It is a smoking gun for a specific type of galactic violence, a dynamic fossil that challenges our models and deepens our understanding of how the universe can mix and match angular momentum in its most dramatic encounters. Now, let's shift our perspective from the isolated beauty of a single ring galaxy to the chaotic, crowded environment of a galaxy cluster. Imagine a celestial metropolis, a region of space teeming with hundreds or even thousands of galaxies, all bound together by gravity in a relatively small volume. In this dense urban environment of the cosmos, the serene, symmetric rings we've been admiring face a constant barrage of threats. The very conditions that make ring formation more likely also make their survival incredibly precarious, turning these clusters into both nurseries and graveyards for these rare structures. The first and most obvious factor is the sheer frequency of interactions. In the vast, empty suburbs of the universe, a galaxy might drift for billions of years without a close encounter. But within a dense cluster, close passes are a regular occurrence. The high population density means the probability of a bullseye collision, the kind needed to create a classic ring galaxy, is significantly higher. It's the difference between driving on an empty country road and navigating a bumper car arena. In the cluster, collisions are not just possible, they are an expected part of galactic life. Astronomers studying clusters like the famous Coma cluster or the Virgo cluster have indeed found a higher proportion of galaxies showing signs of recent, violent interactions, including a number of ring-like structures. This suggests that these crowded environments are efficient factories for creating ring galaxies, constantly forging new ones through a relentless cycle of cosmic fender benders. However, this creative violence comes with a devastating downside: tidal disruption. A ring galaxy is a delicate, dynamically young structure. Its beautiful symmetry depends on a precise balance of forces. But in a cluster, a newly formed ring is immediately surrounded by massive neighbors, each with its own powerful gravitational field. As the ring galaxy orbits the cluster's center, a close flyby from another large galaxy can exert immense tidal forces. These forces act like a cosmic hand grabbing the ring and pulling it apart. They can warp the ring out of its perfect circle, stretch it into an elliptical shape, or even begin to strip stars and gas directly from it, leaving behind a smeared and distorted remnant of its former glory. The same crowded environment that provides the opportunity for the ring's birth also subjects it to a constant gravitational battering that can quickly destroy it. This leads to a fascinating cosmic paradox. While we might expect to find more ring galaxies in clusters due to the higher collision rate, we often find that their lifetimes are drastically shortened. A ring galaxy that forms in an isolated region of space might persist for several 100 million years, its structure slowly evolving in relative peace. But a ring born in a dense cluster might be ripped apart in a fraction of that time. Its brilliant blue pearls of star clusters could be scattered across intergalactic space, becoming part of the cluster's general population of wandering stars. This creates a transient population of ring galaxies in clusters, objects that flash into existence with brilliant intensity, but are just as quickly snuffed out by their hostile surroundings. Detecting them requires luck, as we are catching them in a very brief window of cosmic time between their formation and their impending destruction. The ultimate fate of a cluster ring galaxy is often absorption into the giant elliptical galaxies that typically dominate the hearts of these clusters. Through a process called galactic cannibalism, the largest galaxies in the center gravitationally consume smaller neighbors. A ring galaxy already weakened by tidal interactions is a prime candidate for this fate. Its delicate structure is completely dissolved as it merges with the giant elliptical, its stars added to the vast, disordered swarm. The ring's unique identity is erased, its story ending not with a slow fade but with a violent assimilation. This constant cycle of creation and destruction in galaxy clusters highlights a fundamental aspect of cosmic evolution. Environment is everything. The same physical processes unfold everywhere, but the outcomes are dramatically different depending on whether a galaxy lives a solitary life or is crammed into a dense urban center of the universe. The ring galaxies we see in clusters are the survivors of a relentless gravitational war, their perfect symmetry a testament to a moment of precise violence amidst a sea of chaos. Throughout our exploration, we've seen how ring galaxies are largely products of violence, sculpted by the collisions of mature galaxies. But this leads to a profound and tantalizing question. Could these elegant structures have formed through a more gentle, primordial process, appearing in the infant universe long before galaxies had settled into the forms we recognize today? This speculation takes us to the very frontier of cosmology, to a time when the first structures were assembling out of the raw material of the Big Bang. The idea of a primordial ring galaxy challenges the very definition of the phenomenon, suggesting that the universe's capacity for creating order might be even more innate than we suspected. To imagine this, we must travel back to the cosmic dark ages before the first stars had ignited. The universe was filled with a nearly uniform soup of hydrogen and helium gas laced with dark matter. As slight density fluctuations, seeds planted by the Big Bang, began to grow under gravity, vast clouds of this pristine gas started to collapse. In our standard picture, these clouds fragmented into smaller clumps that eventually merged hierarchically to form the first stars and the proto-galaxies that would become the building blocks of larger galaxies. But what if, under very specific conditions, a different path was taken? What if a particularly large, rapidly rotating cloud of primordial gas collapsed not into a chaotic mess of clumps, but directly into a stable, rotating disk? Instabilities within this vast, featureless disk could, in theory, have triggered a ring of star formation without any external trigger. A gravitational instability, perhaps driven by the specific distribution of dark matter within the halo, could have caused the gas to fragment into a ring-like pattern, igniting the first stars in a perfect circle around a central density. This would be a ring galaxy born not from catastrophe, but from the elegant internal dynamics of a virgin universe. The search for such an object is more than just a hunt for a cosmic fossil. It would be a direct test of our theories about the initial conditions of the cosmos. A primordial ring galaxy would be a relic of a time when physics operated on a purer scale, uncomplicated by the heavy elements and complex magnetic fields that shape modern galaxies. Its stellar population would be incredibly metal-poor, consisting almost entirely of hydrogen and helium, the products of the Big Bang itself. Finding one would suggest that the universe's tendency toward symmetry and order is fundamental, capable of producing complex structures even in its earliest, simplest epochs. It would imply that the potential for a ring galaxy is written into the basic laws of gravity and hydrodynamics, waiting only for the right initial conditions to manifest. This is where the next generation of observatories, particularly the James Webb Space Telescope, enters the story with revolutionary potential. Our current telescopes can see back to the era of the first galaxies, but these early objects are typically just faint red blobs. Resolving their detailed internal structure, like discerning a ring shape, is far beyond their capabilities. The James Webb Space Telescope, with its unparalleled infrared sensitivity and sharp resolution, was built to cross this threshold. It can peer through the dust and redshift that shroud the early universe, not just detecting the first galaxies, but potentially revealing their morphology. The hunt for a primordial ring will involve scanning deep fields for ancient galaxies that exhibit an unusual, extended, and circular light profile. The signature would be subtle, a faint reddish ring of the very first metal-free stars, known as population 3 stars, surrounding an even fainter central glow. Confirmation would require spectroscopic analysis to prove the near-total absence of heavy elements, the smoking gun of a truly primordial origin. Discovering such an object would force a significant rewrite of our models of early structure formation. It would demonstrate that monolithic collapse, the direct formation of a large, ordered disk, could compete with the hierarchical merging of smaller clumps as a pathway for galaxy birth in the early universe. This would have cascading implications for our understanding of how dark matter behaved, how quickly gas could cool, and how efficiently the first stars could form. A primordial ring would stand as a silent sentinel from the cosmic dawn, a testament to a simpler, more ordered path of creation that existed before the universe became a chaotic workshop of collisions and mergers. Its discovery would not diminish the drama of the later collisional rings, but would instead reveal a deeper, more fundamental elegance in the cosmos's design, showing that the universe has always known how to paint with circles of light. In the high-energy environment of a ring galaxy, where massive stars are constantly being born and dying, we find a phenomenon that turns the galaxy itself into a cosmic recording device. Imagine a supernova exploding somewhere within that brilliant blue ring. In an instant, a titanic flash of light radiates outward in all directions, traveling at the ultimate speed. The first light we see is that which travels directly to our telescopes, but the story doesn't end there. That initial burst of light continues to travel, and some of it is heading not toward us, but toward other parts of the ring's vast, complex structure. When this light finally strikes distant clouds of gas and dust within the ring, it can illuminate them, causing them to glow. Because this light has taken a longer, indirect path, we see this illumination months or even years after the original explosion. This is a light echo, a ghostly signature of a past cataclysm that allows us to see the same flash of light multiple times, each time reflected from a different celestial surface. The way this works is analogous to an audio echo in a large canyon. If you shout, the sound waves travel directly to your ears, but they also travel to the far canyon wall, bounce off, and return to you a moment later. A light echo functions on the same principle, but at the speed of light and across distances of thousands of light years. The supernova is the shout, and the filaments and clouds of gas within the ring galaxy are the canyon walls. We observe the initial flash, and then, over time, we see a wave of illumination expand outward through the ring. This isn't a physical wave of energy, it's a wave of light that is progressively lighting up more and more distant structures. The resulting appearance is a series of luminous rings or arcs that seem to expand from the point of the explosion, like ripples from a stone dropped in a pond, but unfolding in incredibly slow motion over years. For astronomers, these light echoes are far more than just a beautiful curiosity. They are a powerful tool for three-dimensional cartography. The key is the finite speed of light. Because we know light travels at a constant speed, we can use the time delay between the initial supernova and the appearance of the echo to calculate precise distances. If an echo appears in a gas cloud 1 year after the supernova, we know that the cloud must be exactly 1 light year farther away from us than the supernova itself. By carefully tracking multiple echoes as they appear in different parts of the ring over several years, we can triangulate the positions of these gas clouds in space. This allows us to build a detailed three-dimensional map of the ring's structure, revealing whether it is a perfectly flat disk, warped or tilted relative to our line of sight. It's a technique that turns the dimension of time into a ruler for measuring depth in space. This mapping capability is revolutionary because it solves a fundamental problem in astronomy, determining the true geometry of distant objects. When we look at a ring galaxy, we see a flat, two-dimensional projection on the sky. It's incredibly difficult to know if the ring is a thin, knife-edged disk or a thick, sausage-like tube. Light echoes remove this ambiguity by showing us which gas clouds are in the foreground and which are in the background relative to the supernova. They reveal the ring's full shape. This three-dimensional information is crucial for understanding the physics of the original collision. For instance, if the ring maps out as a warped structure, it suggests the intruder galaxy hit at an angle rather than a perfect bullseye. If it is remarkably flat, it confirms a very direct and symmetric impact. Each echo is like a surveyor's stake, helping us plot the true topography of this cosmic structure. A famous example of this occurred not in a ring galaxy, but within our own Milky Way with the supernova that created the Crab Nebula. Historical records from the year 1064 document a guest star that was visible in the daytime. Centuries later, astronomers observed light echoes still expanding outward from the site of that explosion, illuminating interstellar dust clouds that were unseen before. This same principle applied to a ring galaxy is even more powerful. There, we have a rich, structured environment filled with gas clouds just waiting to be lit up. By patiently monitoring a ring galaxy after a supernova, astronomers can watch as the echo propagates, revealing the intricate architecture of the stellar nursery in stunning detail. It is a patient, years-long observation that rewards us with a depth of understanding impossible to gain from a single snapshot, turning a fleeting stellar death into a lasting probe of the galaxy's deepest secrets. But beyond mapping the galaxy's structure, these brilliant stellar explosions can also illuminate a far more subtle and speculative mystery, one that ventures into the realm of exotic physics and questions about the fundamental imbalance of the universe itself. When a massive star in the ring goes supernova, it does more than just create a light echo. It becomes a natural particle accelerator of almost unimaginable power, and some theories suggest that within these fiery crucibles, conditions might be ripe for the creation of one of the universe's most elusive substances, antimatter. This leads to a fascinating, though currently unproven, idea that ring galaxies could be ideal hunting grounds for a signal that has so far remained undetected. To understand this, we need to revisit what antimatter is. For every type of normal matter particle like an electron or a proton, there is an antimatter counterpart with the same mass but an opposite electric charge. When a particle meets its antiparticle, they annihilate each other in a flash of pure energy, typically emitting gamma rays, the most energetic form of light. The great cosmic puzzle is that our observable universe appears to be made almost entirely of matter. Why there is this profound asymmetry, why antimatter is so exceedingly rare, is one of the biggest unsolved problems in physics. So, if a process were to create significant amounts of antimatter anywhere in the contemporary universe, it would be a monumental discovery. The unique environment of a ring galaxy's star-forming front makes it a compelling candidate to search for such a signal. The supernova and the powerful stellar winds from massive stars create a turbulent, high-energy environment. Certain speculative theories propose that under these extreme conditions, perhaps involving the interactions of cosmic rays or processes near rapidly spinning neutron stars, there could be mechanisms that produce more antimatter than we typically observe in such events. If this were happening, we would expect to detect a specific and anomalous signature, a telltale glow of gamma rays at very specific energy levels, precisely those that correspond to the annihilation of electrons with their antimatter twins, positrons. Astronomers have used powerful instruments like the Fermi Gamma Ray Space Telescope to scan the skies for this exact signal, and ring galaxies are among the targets. The logic is sound. If antimatter is being produced in these stellar factories, the sheer concentration of supernova in the ring should make it a relatively bright source of these characteristic gamma rays. However, despite careful searches, no conclusive evidence has been found. The gamma ray signals from ring galaxies appear consistent with what we would expect from normal, though incredibly violent, astrophysical processes alone. The missing antimatter signal remains missing. This absence of evidence is in its own way just as informative as a detection would be. It places stringent limits on these exotic theories. It tells us that if such particle processes are occurring, they are either far less efficient than some models predicted, or they are buried under the overwhelming gamma ray background produced by more conventional means. The quietness of ring galaxies in gamma rays reinforces the standard model of particle physics, which does not predict large-scale antimatter production in these environments. It forces physicists to look for other, even more exotic explanations for the matter-antimatter asymmetry, perhaps involving conditions that existed only in the very first moments after the Big Bang. So, while the search has so far come up empty, it continues. Each new generation of telescopes with greater sensitivity will look again because the potential reward, a glimpse of physics beyond our current understanding, is worth the long and patient search. The silent gamma ray sky above these rings is a testament to the universe's stubborn adherence to its known rules, even as it challenges us with its deepest mysteries. We've seen how ring galaxies can act as cosmic lenses and even as potential antimatter factories, but these stellar powerhouses may also be responsible for accelerating some of the most energetic particles in the entire universe. All around us, space is constantly bombarded by cosmic ray subatomic particles, mostly protons and atomic nuclei, traveling at nearly the speed of light. For over a century, scientists have been trying to pinpoint the exact sources of these high-energy projectiles, and the violent, expanding shock waves that carve out galactic rings are now considered prime suspects in this cosmic mystery. The process begins with the same expanding density wave that triggers the ring of star formation. This isn't just a gentle ripple, it's a supersonic shock front racing through the galaxy's interstellar medium. As this colossal wall of pressure moves outward, it creates a region of incredibly turbulent magnetic fields. Charged particles like protons and electrons that were already drifting in space can become trapped by these magnetic fields. They get caught in the shock wave, bouncing back and forth across its leading edge as if caught in a cosmic ping-pong game. With each crossing, the magnetic turbulence of the shock transfers a small amount of energy to the particle, accelerating it to a higher speed. Over many iterations, this process, known as diffusive shock acceleration, can boost particles to energies far beyond anything achievable in human-built particle colliders like the Large Hadron Collider. What makes a ring galaxy's shock front such an effective accelerator is its sheer scale and longevity. Unlike a supernova remnant whose shock wave expands and fades over thousands of years, the shock front in a ring galaxy can be sustained for tens of millions of years. It propagates outward at a steady pace, driven by the gravitational aftermath of the collision rather than a single, short-lived explosion. This provides a vast and long-lived arena for particles to be accelerated. The entire circumference of the ring acts as a continuous, natural particle collider tens of thousands of light-years across, potentially capable of producing cosmic rays of the very highest energies observed. The challenge for astronomers is connecting these distant events to the particles that rain down on Earth. Because cosmic rays are charged particles, their paths are bent by the Milky Way's magnetic fields as they travel. By the time they reach our detectors, it's impossible to trace them back directly to their point of origin. They arrive from all directions equally. So instead of tracing individual particles, scientists look for a smoking gun, high-energy gamma rays. When an ultra-high-energy cosmic ray proton accelerated in a ring galaxy collides with a proton in a cloud of interstellar gas, the interaction can produce a neutral pion, which almost instantly decays into a pair of gamma-ray photons. These gamma rays travel in straight lines, unaffected by magnetic fields. If we can detect a distinct signature of gamma rays coming from the shock front of a ring galaxy, it will be powerful, indirect evidence that the site is indeed a powerful cosmic ray accelerator. This places ring galaxies as key players in a broader astrophysical puzzle. They may help explain the origin of the mysterious Ni in the cosmic ray energy spectrum, a point where the number of particles at a given energy drops off sharply. Some models suggest that supernova remnants within our own galaxy can accelerate particles up to the energy of this Ni, but to reach even higher energies, we may need the more powerful and sustained shocks found in extragalactic sources like ring galaxies. If confirmed, this would mean that the highest energy particles striking our atmosphere began their journey in a cataclysmic collision millions of light years away. Their incredible energy a testament to the violent forces that shape these beautiful cosmic rings. Moving outwards from the protective embrace of its own galactic material, the expanding ring of a galaxy must eventually push against the vast, almost empty expanses that separate island universes. This space is not a perfect vacuum. It is filled with the intergalactic medium, an incredibly thin soup of ionized gas and dark matter that constitutes the true backdrop of the cosmos. While this medium is so diffused that it would be considered an ultra-high vacuum in any laboratory on Earth, when an entire galaxy structure moves through it at tremendous speeds, this tenuous substance becomes a significant force, sculpting the ring in subtle but profound ways. Picture a powerful speedboat racing across a calm lake. As the boat's hull cuts through the water, it doesn't just slide through effortlessly. It pushes the water aside, creating a visible bow wave at its front and leaving a churning wake behind it. The ring of a galaxy, as it expands outward, acts in a remarkably similar fashion. The ring is not static. It is a coherent structure plowing through the intergalactic medium at speeds that can reach hundreds of kilometers per second. The gas in the ring rams into the even more tenuous gas of the intergalactic medium, compressing it and creating a shock front, a cosmic bow wave that can, in some cases, be detected as a faint ultraviolet glow. This is not a wave of water, but a wave of heated, pressurized gas marking the leading edge of the ring's journey into the cosmic void. This interaction can have a significant erosive effect on the ring itself, a process known as ram pressure stripping. The force of the impact, like a constant, powerful headwind, can literally blow gas and dust right out of the ring. Imagine the boat's deck is covered in loose leaves. As it accelerates, the wind rushing past will strip those leaves away. In the same way, the intergalactic medium exerts a pressure that can overcome the ring's own gravitational pull on its most loosely bound material. This is particularly effective at removing the very fuel that powers the ring's brilliant star formation, the cold, dense clouds of hydrogen gas. Over millions of years, this relentless stripping can starve the ring, quenching its stellar baby boom prematurely and leaving behind a skeleton of stars that will slowly fade. The intergalactic medium, in this role, acts as a cosmic sandblaster, slowly wearing down the ring's most vital components. The visibility of this interaction provides astronomers with a unique tool for measuring the galaxy's motion through space. By studying the shape and intensity of the bow shock, scientists can determine the direction and speed at which the ring galaxy is moving relative to its surroundings. A strong, symmetrical bow shock indicates a direct, head-on motion into the medium. A skewed or curved shock front suggests the galaxy is moving at an angle, or that the intergalactic medium itself is not uniformly distributed but flows in large-scale currents. Furthermore, the presence of a long, trailing wake of stripped material behind the galaxy, much like the boat-churning trail, can be a telltale sign of its passage, a ghostly signature visible only to the most sensitive radio and X-ray telescopes. This allows us to map not just the galaxy, but the invisible currents of the cosmic ocean it is navigating. The ultimate impact of the intergalactic medium depends heavily on the galaxy's environment. A ring galaxy living in splendid isolation, moving through a relatively quiet region of space, might experience only mild stripping, allowing its ring to shine for a longer period. However, a ring galaxy born within a dense galaxy cluster faces a far more hostile environment. The space within clusters is filled with a much hotter, denser intergalactic medium known as the intracluster medium. Plowing through this hot gas is like moving from a calm lake into a churning, stormy sea. The ram pressure is immensely stronger, and the stripping process can be devastatingly efficient, rapidly tearing the ring apart and contributing to the galaxy's transformation into a more common, featureless elliptical shape. The fate of the ring is therefore not sealed solely by the initial collision. It is continually shaped by its ongoing dialogue with the vast, invisible ocean of gas that fills the universe. Just when we thought the cosmos had exhausted its capacity for surprise, we encounter a configuration so rare it seems to defy all odds, a pair of ring galaxies locked in a gravitational dance. Imagine the Cartwheel Galaxy, but then picture another perfect ring of similar size and brilliance floating nearby, with faint tidal streams stretching between them like cosmic bridges. This is not a mere artistic concept. A handful of these binary ring systems have been tentatively identified, and their existence pushes our understanding of galactic collisions into a realm of staggering improbability and dynamical chaos. The sheer statistical unlikelihood of such a pairing is the first layer of the mystery. Forming a single ring galaxy requires a very specific set of circumstances, a bullseye collision between two galaxies. For two such galaxies to form and then find themselves close enough to interact adds another layer of astronomical chance. It's the cosmic equivalent of two skilled archers standing miles apart, each firing an arrow that hits the exact center of the other's target simultaneously. The conditions are so precise that these binary systems are incredibly rare, making each candidate a precious natural laboratory for testing the most extreme models of galactic evolution. The dynamics of such an interaction are a recipe for gravitational pandemonium. Each ring is a delicate structure, a temporary phase in a galaxy's life. Now, subject that delicate structure to the powerful, chaotic tidal forces of a nearby galaxy that is itself a delicate ring. The gravitational pull from the companion galaxy would warp and distort both rings, potentially triggering new, secondary bursts of star formation at the points of greatest stress. The clean, symmetric density waves that created each ring would now be interacting, creating complex interference patterns. Computer simulations of such a system show a spectacularly messy outcome. The rings can be pulled into elliptical shapes, they can develop spiral-like features, or they can even begin to shear apart, their stars being drawn out into vast, intersecting tidal tails that weave the two galaxies together into a single, tangled web of starlight. Studying such a system would provide an unprecedented test for the stability and longevity of ring structures. We've discussed how a single ring might last for a few 100 million years before fading. But what happens when you put two rings on a collision course? Does the mutual gravitational disturbance cause them to dissolve much faster, shredding each other in a cosmic feedback loop of destruction? Or could their interaction under some very specific conditions actually stabilize them? Perhaps their gravitational fields could find a resonant balance, a fragile harmony that allows both rings to persist for longer than they would in isolation. Observing a real binary ring system would allow us to measure this directly, giving us a clock for ring longevity under the most extreme duress. Beyond stability, these systems offer a unique window into the distribution of dark matter. We can use the motion of the two galaxies as they orbit each other to weigh the entire system. But more importantly, by observing how the visible rings are distorted by their mutual gravity, and comparing that to the overall orbital motion, astronomers could map the extended dark matter halos of both galaxies with incredible precision. Any discrepancy between the visible distortion and the expected gravitational pull would reveal the hidden hand of the dark matter, potentially showing how these invisible halos are shaped and how they interact during a slow-motion merger of two already bizarre objects. The ultimate fate of a binary ring galaxy is almost certainly a merger, but what a merger it would be. It wouldn't be the collision of two serene spiral galaxies. It would be the confluence of two systems that are already the products of immense violence. The result would likely be a hyper-energetic starburst of unimaginable scale, as the gas reservoirs of both rings are compressed simultaneously, followed by the complete destruction of both ring structures. The final product would probably be a massive elliptical galaxy, but one with a uniquely complex history written into the chemical composition and motions of its stars. Each binary ring system is therefore a snapshot of the universe in its most creatively destructive mood, a fleeting moment where two circles of fire orbit each other before culminating in a final act of cosmic alchemy that forges a new galactic identity from the ashes of two extraordinary pasts. Now, let's shift our focus from the violent origins and dynamic structures to a more subtle, yet profoundly telling, transformation that unfolds over millions of years. The brilliant blue firestorm that defines a young ring galaxy is not a permanent feature. It is a fleeting, vibrant youth destined to fade into a more serene old age. This inevitable shift in color from a searing blue to a softer yellow and eventually a deep red is far more than an aesthetic change. It is a cosmic clock, meticulously ticking away the time that has passed since the galaxy's cataclysmic rebirth. The color of the ring is a direct readout of the age of its stellar population, providing astronomers with one of the most reliable methods for dating the original collision event. This color evolution is governed by the simple, unyielding rules of stellar physics. The intense blue-white light of a young ring comes from O and B-type stars. These are the titans of the stellar world, many times more massive than our own sun. Their immense mass creates tremendous pressure and temperature at their cores, causing them to burn through their nuclear fuel at a ferocious rate. They live fast and die young, shining with a brilliant blue light for only a few million years before ending their lives in spectacular supernova explosions. When you look at that blue ring, you are essentially looking at a single, synchronized generation of stellar giants, all born in the same brief burst of activity. Their collective color is so dominant that it defines the entire visual character of the galaxy. As these massive stars rapidly exhaust their fuel and explode, they begin to drop out of the stellar population. The first to go are the very largest, the ones that burn the hottest and bluest. Their disappearance shifts the overall balance of light emitted by the ring. The stars that remain are the smaller, less massive ones, the A-type, F-type, and G-type stars, which are yellow or white in color, similar to our Sun. These stars have much longer lifespans, measured in billions rather than millions of years. As the last of the blue supergiants vanish, the ring's color transitions from its initial brilliant blue to a more golden or yellowish hue. This is the galaxy's middle age, a period where the frantic pace of youth has given way to a more sustained glow. Given enough time, even the yellow stars will begin to fade from prominence. The longest-lived stars in the universe are the small, cool, red dwarfs, but they are also incredibly faint and do not contribute much to a galaxy's overall light. The stars that will eventually dominate the light of an ancient ring are the red giants. These are older, mid-sized stars like our Sun that have exhausted the hydrogen fuel in their cores and have expanded to enormous sizes, cooling down and glowing with a distinctive red light. After hundreds of millions to billions of years, the ring will be populated largely by these red giants and the fading embers of longer-lived dwarf stars. The entire structure will thus appear a deep, somber red, a ghostly echo of the brilliant firestorm it once was. This predictable sequence of color change allows astronomers to act as cosmic forensic scientists. By carefully measuring the color of the ring, comparing its brightness in blue filters to its brightness in red or infrared filters, they can calculate the average age of the stars within it. If the ring is still a vivid blue, the collision must have occurred very recently, perhaps within the last 50 million years. A ring that appears white or yellow suggests an older system with an age of 100 to 500 million years. A red ring indicates a truly ancient collision, one that happened over 1 billion years ago. This technique provides a direct and relatively straightforward way to pin a date on the most dramatic event in the galaxy's history, turning its color into a precise chronological tool. The real power of this method is revealed when combined with other observations, such as the ring's expansion velocity. By knowing how fast the ring is moving outward and measuring its current size, astronomers can calculate how long it has been expanding. If this dynamical age matches the stellar age inferred from the color, it provides a powerful cross-check confirming the models of how ring galaxies form and evolve. Discrepancies, however, can be even more revealing. If the stars appear older than the expansion velocity suggests, it might mean the collision was more complex than a simple bullseye, or that the ring has been slowed by interactions with unseen dark matter. The color of the ring is therefore not just a passive clock. It is an active diagnostic, a key piece of evidence in the ongoing investigation to understand the full story of these magnificent cosmic structures, from their violent birth to their quiet, fading retirement. But what if that perfect cosmic circle is broken? We've been picturing these rings as flawless, unbroken bands of light, but nature often prefers imperfection. Some ring galaxies present us with a startling sight. A brilliant arc of blue stars that simply stops, leaving a vast dark gap before resuming on the other side. Instead of a continuous wedding band, we see a celestial necklace with a clasp missing, a structure that raises new and fascinating questions about the chaotic forces that shape them. These asymmetric gaps are more than just blemishes. They are profound clues pointing to a much messier and more dynamic formation process than a simple, clean collision. The most straightforward explanation for a broken ring lies in the nature of the intruder itself. Our model of a perfect bullseye collision assumes the smaller galaxy is a uniform, symmetric object. But what if it wasn't? Galaxies are lumpy, filled with clusters of stars and clouds of gas of varying densities. If the intruder galaxy had an uneven structure, perhaps a particularly dense core of a satellite galaxy within it, or a large, empty void, this irregularity would be imprinted directly onto the shockwave it created. As it passed through the center, the densest part of the intruder would deliver a stronger gravitational kick, creating a more powerful compression in one part of the ring. Conversely, a less dense region would create a weaker shock. This uneven push could result in a ring that forms strongly in some sectors and barely at all in others, leaving behind a gap where the triggering impulse was too feeble to ignite significant star formation. The ring, in this case, becomes a direct map of the intruder's internal structure, a fossilized record of its lumpiness. Another compelling theory involves a second act of violence after the ring has already formed. Imagine a ring galaxy, its perfect circle freshly ignited, beginning its slow expansion. Then, a small dwarf galaxy, or even a massive globular cluster, ventures too close on a trajectory that takes it right through a section of the ring. The gravitational tide from this passerby could be enough to disrupt the delicate ring structure locally. It could pull the gas and young stars out of their orderly orbit, scattering them and effectively punching a hole in the ring. The intruder might even steal material from the ring, pulling it away into a tidal stream. This would create a gap that is not a relic of the ring's formation, but a later injury inflicted upon it. The presence of a small companion galaxy near the gap would be a strong piece of evidence for this ring-piercing hypothesis. We must also consider the possibility that the gap grew from within. The ring itself is a dynamic structure, not a static sculpture. Gravitational instabilities can work on it over time. Certain sections of the ring, if they become slightly denser than others, might collapse inward on themselves faster, consuming the available gas and forming stars more rapidly. Once the massive stars in that segment explode as supernova, they could blow the remaining gas away, effectively shutting down star formation in that part of the ring and leaving a dark gap between two still active regions. Alternatively, instabilities could cause the ring to fragment into distinct glowing knots, a string of pearls, and if the fragmentation is uneven, the gaps between the pearls could be exceptionally large, creating the appearance of a broken circle. The ring's own struggle to maintain its coherence against the relentless pull of gravity can tear it apart from the inside out. The search for the true cause of these gaps is an active area of research, and the answer likely depends on the specific galaxy in question. By studying the detailed properties of the gap, is the region completely empty of gas, or is there faint ionized gas that simply hasn't formed stars? Are the stars on either side of the gap different ages? Astronomers can distinguish between the theories. A gap devoid of all material points to a primordial flaw in the shockwave or a disruptive secondary encounter. A gap containing hot, shocked gas but no young stars suggests an internal instability where conditions simply never reach the critical density for collapse. These broken rings remind us that the universe is a place of immense complexity, where even the most beautiful and symmetric structures are born from and shaped by a turbulent and often messy reality. And as our exploration of these 50 phenomena has shown, the universe is filled with more strange and wonderful ring galaxies than any single team of professional astronomers could ever hope to study on their own. This brings us to a truly remarkable and heartening aspect of modern science, one that proves you don't need a PhD or access to a mountaintop observatory to make a genuine contribution to our understanding of the cosmos. This is the world of citizen science, and specifically, the incredible success of projects like Galaxy Zoo, which have turned the search for celestial oddities into a collaborative effort that spans the globe, harnessing the curiosity and pattern recognition skills of hundreds of thousands of volunteers. The story of Galaxy Zoo begins with a simple problem of overwhelming abundance. Digital sky surveys, like the Sloan Digital Sky Survey, began automatically imaging vast swaths of the night sky, generating a database of millions of galaxies. For a small team of researchers, classifying each one of these galaxies by its shape, spiral, elliptical, irregular, or something more unusual was an impossible task. It would have taken a lifetime, so in 2007, a group of astronomers had a revolutionary idea. Why not ask the public for help? They built a website where anyone with an internet connection could log on, be shown an image of a galaxy, and answer a series of simple questions about its appearance. The goal was to crowdsource the classification of 1 million galaxies, a monumental undertaking that, to the astonishment of the scientific community, was completed in just over a year thanks to the incredible enthusiasm of volunteers. What started as a solution to a data problem blossomed into a new paradigm for scientific discovery. It is within this vast digital catalog that ring galaxies, those rare celestial gems, began to stand out. The human brain is exceptionally good at recognizing patterns, especially unusual ones that might be missed by even the most sophisticated computer algorithm. A computer program might be trained to identify a perfect ring, but what about a warped ring, a broken ring, or a ring within a ring? It is the intuitive spark of a human volunteer, often an amateur astronomer or simply a curious individual, that can look at a strange, fuzzy patch of light and think, "That doesn't look like anything else I've seen." Countless unusual ring galaxies, including many of the peculiar types we've discussed in this very video, were first flagged not by a professional in an institute, but by a teacher, a retiree, or a student spending their evening exploring the universe from their living room. The contributions of these citizen scientists are far from superficial. There are powerful, documented stories of amateurs making discoveries that have led to published scientific papers. One of the most famous examples from Galaxy Zoo is Hanny's Voorwerp, a strange, glowing green object of ionized gas discovered by Dutch schoolteacher Hanny van Arkel. While not a ring galaxy itself, this discovery showcases the potential for volunteers to stumble upon entirely new classes of astronomical objects that professionals had overlooked. In the realm of rings, volunteers have identified galaxies with multiple rings, rings that are kinematically misaligned, and systems so bizarre they defy easy classification, often sparking follow-up observations with major telescopes like Hubble. These volunteers become partners in the research, with their usernames frequently acknowledged in the credits of scientific papers, a testament to their vital role. This collaborative model has fundamentally changed the relationship between professional astronomy and the public. It has democratized discovery, proving that the frontier of knowledge is open to anyone with curiosity and a willingness to learn. Projects like Galaxy Zoo have spawned numerous offshoots, creating a whole zooniverse of projects where the public can hunt for planets, transcribe ancient weather records, or classify the calls of whales. In the context of ring galaxies, this means there are now more eyes than ever before scanning the skies, each volunteer a potential pioneer. The next great cosmic mystery, the next Hoag's object or Cartwheel Galaxy, might not be found by a scheduled observation on a multi-billion-dollar telescope, but by a sharp-eyed volunteer on their lunch break, reminding us all that the drive to explore and understand the universe is a deeply human trait, one that connects us all under the same starry sky. To truly understand the cataclysmic birth of a ring galaxy, we must venture beyond the telescope and into the realm of pure computation. The static, beautiful images we see are just a single frame in a billion-year-long movie. To watch the entire film, astronomers rely on some of the most powerful supercomputers on Earth. These machines are virtual time machines, allowing us to rewind the cosmic clock, set up initial conditions, and let the immutable laws of physics play out over eons in a matter of days or weeks. Simulating the formation of a ring galaxy is an intricate dance of gravity, hydrodynamics, and stellar feedback, a digital experiment where we can test our theories with breathtaking precision. The foundation of any simulation is its initial setup, and for a ring galaxy, this means defining two key characters, the target galaxy and the intruder. The target is typically a stable disk galaxy, similar to the Milky Way, modeled with a rotating disk of stars and gas, a central bulge, and crucially, a massive, invisible halo of dark matter that provides the gravitational scaffolding for the entire system. The intruder is often a smaller, gas-rich dwarf galaxy. The scientist then assigns the critical parameters of the encounter, the relative masses of the two galaxies, the speed at which the intruder is moving, and perhaps most importantly, the angle of its approach. A change of just a few degrees in this angle can mean the difference between creating a perfect ring and producing a messy, irregular galaxy. Once the parameters are set, the simulation begins. Billions of particles, each representing a cloud of stars or a parcel of gas, are set in motion according to the equations of gravity and fluid dynamics. The visualizations that result are both beautiful and violently instructive. In a successful ring-forming simulation, you watch as the intruder galaxy, like a bullet, plunges directly through the center of the target's disk. The gravitational shockwave is instant and dramatic. It doesn't shatter the disk like glass. Instead, it acts like a pebble dropped in a pond, sending a circular density wave racing outward. This wave is visible as a ripple of compressed gas, and it's precisely at this leading edge that the simulation begins to light up with new stars, mirroring the brilliant blue rings we observe in nature. The power of simulation lies in its ability to explore the what-ifs. What if the collision isn't a perfect bullseye? When scientists run a simulation with an oblique angle, the results are strikingly different. The intruder's glancing blow delivers an off-center gravitational kick, which often produces a lopsided or broken ring, or even a single grand spiral arm instead of a closed circle. This helps explain the many asymmetric ring structures we see, demonstrating that not every encounter is perfectly aligned. Similarly, varying the speed of the intruder has profound consequences. A high-speed encounter might create a clean, rapidly expanding ring as the intruder zips through and escapes, leaving behind a wounded but intact target. A slow, ponderous collision, on the other hand, is more like a merger. The two galaxies become gravitationally entangled, their structures torn apart into long tidal tails, often resulting in a chaotic mess rather than a pristine ring. These virtual experiments are not just about creating pretty pictures, they are essential for interpreting real-world data. When astronomers observe a ring galaxy like the Cartwheel, they can measure its expansion velocity and the age of its stars. They can then go to their simulations and ask, which set of initial parameters, which specific mass, speed, and angle, produces a virtual galaxy that matches these exact observed properties. It's a process of cosmic fingerprint matching. When a simulation successfully recreates a known ring, it gives us tremendous confidence that we understand the physics of the collision that created it. Furthermore, simulations have been pivotal in exploring alternative formation theories, such as resonance-driven rings, showing that under the right conditions, a galaxy can indeed create a ring from within without any external trigger. By running these countless digital experiments, supercomputers have transformed ring galaxies from static celestial wonders into dynamic, evolving characters in the grand story of the universe, allowing us to witness their violent birth and predict their eventual fate. But what happens when the source of the ring is not a collision of galaxies, but an eruption of energy so violent it can outshine an entire galaxy? We now turn to one of the most extreme and luminous objects in the cosmos, the quasar. These are not galaxies in the traditional sense, but the fiercely bright cores of distant galaxies, powered by supermassive black holes in a frenzied state of feeding. For decades, quasars were studied as brilliant points of light. Yet, as our observational techniques have sharpened, we've begun to pierce the glare, and in doing so, have uncovered a stunning secret. Some quasars are surrounded by vast, ring-like structures. This discovery forces us to ask a radical question. Can a ring be forged not by gravity, but by light itself? The immediate challenge in understanding these rings is separating cause from effect. In a classic ring galaxy, the sequence is clear. A collision triggers a density wave which compresses gas to form a ring of stars. But with a quasar, we are dealing with an object that is a perpetual cosmic hurricane. Its central engine, a black hole weighing billions of suns, is actively devouring matter. As gas spirals into the black hole, a T, Chinese letter, the speed of light, it forms an accretion disk heated to millions of degrees, blasting out enough radiation to push surrounding material away. One compelling theory suggests that these quasar rings are not stellar nurseries at all, but are instead the ghostly imprints of this incredible feedback. The quasar's radiation, along with powerful jets of particles, could be acting like a cosmic sandblaster, excavating a vast cavity in the galaxy's gas reservoir. What we see as a ring might be the illuminated inner wall of this bubble, a shell of gas that has been compressed and set aglow by the quasar's relentless outflow, rather than by a gravitational wave. However, the story may not be so simple. Could it be that the quasar and the ring share a common, violent origin? Another fascinating possibility is that the same colossal collision that triggered the quasar's feeding frenzy also created the ring. Imagine a massive merger of two gas-rich galaxies. The chaotic event funnels a tremendous amount of gas toward the central black hole, igniting the quasar. Simultaneously, the gravitational shockwaves from the merger could propagate outward, triggering a classic ring of star formation. In this scenario, the ring and the quasar are siblings born from the same cataclysm. The quasar provides the brilliant central spotlight, while the collision provides the ringed structure. Distinguishing between this collisional ring model and the feedback ring model is a major focus of current research, and the key lies in the details of the ring's light. Astronomers tackle this mystery by dissecting the ring's light with spectrographs. If the ring is primarily composed of young, hot stars like the blue rings we've seen elsewhere, its spectrum will show the specific absorption lines of those stars. This would strongly support the collisional origin, indicating the ring is a true stellar structure. If, however, the ring's light is dominated by the characteristic emission lines of ionized gas, the same kind of glow seen in nebulae heated by a nearby star, it would point toward the feedback model. In this case, the ring is not a collection of stars, but a colossal cloud of gas that is being illuminated and heated by the quasar's intense ultraviolet radiation, much like a neon sign. Early observations suggest a complex picture. Some quasar rings show evidence of both processes, indicating that a past collision may have created the ring, which is now being further shaped and illuminated by the awakened monster at the galaxy's heart. The existence of these rings around quasars provides a unique probe into the most energetic phase of a galaxy's life. The ring acts as a visible marker for the immense power of quasar feedback. By measuring the size of the ring, astronomers can estimate the total energy the quasar has injected into its surroundings. A larger ring implies a more powerful or longer-lasting outburst. This helps us understand how these active black holes eventually shut down their own fuel supply by blowing away the surrounding gas, a process thought to be crucial for the evolution of massive galaxies. Furthermore, because quasars are so incredibly bright, we can see them at phenomenal distances, corresponding to a time when the universe was young. Finding rings around these early quasars would suggest that such structured feedback was already in operation billions of years ago, playing a fundamental role in shaping galaxies from the very beginning. The ring around a quasar is therefore more than a pretty halo. It is a fossilized record of the most powerful eruptions in the universe, a temporary monument to the brief, brilliant reign of a supermassive black hole. This cosmic detective story now takes us on a hunt for the missing perpetrator. We have the beautiful, wounded ring galaxy, the clear evidence of a violent crime, but in many cases the culprit appears to have fled the scene. The search for this so-called intruder galaxy is a critical part of piecing together the complete narrative of the ring's birth. It's not enough to know that a collision happened. To fully understand the event, astronomers need to find the other key participant, often a smaller galaxy that has since traveled a great distance on its original trajectory. The methods for this search are as ingenious as they are challenging. Astronomers act as celestial surveyors, carefully mapping the space surrounding the ring galaxy. They are looking for two possible clues. The first is the intruder galaxy itself, which may have escaped the gravitational pull of the larger galaxy and is now a faint, separate system drifting millions of light years away. Identifying it requires painstakingly studying every small, faint galaxy in the vast neighborhood, looking for one that shows signs of recent trauma. Perhaps a disturbed shape or a trail of stripped stars that would link it to the encounter. The second, and often more telling clue, is a tidal tail or stellar stream. As the intruder galaxy passed by, its gravitational pull would have stretched the larger galaxy, ripping out long, faint arcs of stars and gas that stretch away from the ring like cosmic breadcrumbs. These immense, ribbon-like structures can persist for billions of years, pointing directly back along the intruder's escape path. A perfect example of a successful manhunt involves the Cartwheel Galaxy. After studying its spectacular ring for years, astronomers identified two smaller companion galaxies located nearby. One of them shows clear signs of recent star formation, suggesting it was the gas-rich dwarf that plunged through the Cartwheel's center. The gravitational interaction stretched this intruder, and we now see it as a distorted galaxy still linked to the Cartwheel by a faint bridge of stars, a permanent leash connecting the perpetrator to its cosmic crime. In other cases, like the beautiful Hoag's object, the intruder remains frustratingly elusive. The perfect symmetry and clean gap of Hoag's object suggest the intruder may have been a high-speed projectile that escaped completely, leaving behind no obvious trail, its identity lost to the depths of intergalactic space. Finding the intruder is about more than just solving a mystery. It completes the physical model of the collision. By measuring the intruder's current distance and velocity, astronomers can rewind the cosmic clock with incredible precision. They can calculate the exact speed and angle of the impact that occurred hundreds of millions of years ago. This allows them to run ultra-detailed computer simulations that replicate the observed ring almost perfectly, confirming our understanding of the gravitational physics involved. Furthermore, studying the intruder tells us about the raw materials involved. Was it a gas-rich dwarf whose fresh hydrogen fuel contributed to the ring's brilliant blue stars? Or was it a barren, elliptical galaxy whose passage caused a gravitational disturbance but added little new material? The ghost of the intruder galaxy, whether found or still missing, holds the final pieces of the puzzle, transforming the ring from a beautiful static object into a dynamic chapter in an ongoing celestial story. Now, let's delve into one of the most profound and speculative connections in modern astrophysics, the potential link between the violent collisions that form ring galaxies and the faintest ripples in the fabric of spacetime itself, gravitational waves. We've already explored how a galactic bullseye impact can trigger a brilliant ring of star formation and awaken a supermassive black hole at the galaxy's core. But when two galaxies merge, their central black holes are destined for a dramatic partnership. If both galaxies harbored a supermassive black hole, the collision could bring these monsters together, locking them into an orbital dance that culminates in the most powerful emission of gravitational waves in the universe since the Big Bang. The journey of these black holes toward merger is a story of cosmic friction. After the initial galactic collision, the two black holes, each weighing millions or even billions of times the mass of our Sun, will sink toward the center of the newly formed system through a process known as dynamical friction. They tug on the surrounding stars and dark matter, which in turn slow them down, causing their orbits to decay. For a time, they may form a binary pair whirling around each other at a fraction of the speed of light. It is in this final, intimate dance that they become a potent source of gravitational waves. According to Einstein's theory of general relativity, any accelerating mass warps spacetime, and a binary black hole system, with its incredibly rapid and asymmetric motion, creates ripples that propagate outward at the speed of light, stretching and compressing space itself as they travel across the cosmos. The gravitational waves produced by such a system would be of an extremely low frequency, with wavelengths measured in light years. These are not the high-frequency waves detected by ground-based observatories like LIGO from the mergers of stellar mass black holes. The oscillations from a binary supermassive black hole would be far too long and slow for any Earth-based instrument to perceive. It would be like trying to detect the gentle, years-long undulation of the ocean floor with a buoy designed to measure sudden, crashing waves. To hear this deep, cosmic hum, we need to go to space. This is the primary mission of future observatories like the Laser Interferometer Space Antenna, or LISA. Planned for launch in the next decade, LISA will consist of 3 spacecraft flying in a triangular formation millions of kilometers apart, connected by lasers. By precisely monitoring the distances between them, it will be able to detect the infinitesimal stretching of space caused by passing low-frequency gravitational waves. A ring galaxy could provide an ideal laboratory for this new astronomy. If the merger that created the ring also left behind a binary supermassive black hole in its core, the gravitational wave signal would carry a unique fingerprint. The frequency and amplitude of the waves would tell us the masses of the black holes and how close they are to merging. By correlating a detected wave signal with the optical image of a ring galaxy, we could directly link a specific type of galactic collision, a bullseye impact, to the dynamics of black hole pairing and merger. This would answer critical questions about how quickly supermassive black holes can coalesce after a galactic merger, and whether the unique environment of a ring galaxy accelerates or hinders this process. The implications of such a detection would ripple across cosmology. First, it would provide direct dynamical evidence for the hierarchical model of galaxy formation, which posits that large galaxies grow through mergers. Second, it would allow us to census the population of binary supermassive black holes in the universe, which is currently very difficult to observe with light alone. Third, and most profoundly, it would open a new window into testing general relativity in the strongest gravitational fields imaginable, probing physics in a regime completely inaccessible by any other means. The silent, dark cores of ring galaxies, which may appear quiet in every wavelength of light, could be broadcasting a vibrant symphony in gravitational waves, a hidden narrative of colossal forces waiting for the right instruments to finally listen. Just when we think we have the life story of a ring galaxy neatly mapped out, a single violent collision, a burst of youthful stars in the ring, and a quiet, ancient core, the universe presents us with an object that turns this entire timeline on its head. Enter LEDA 1000714, a galaxy that looks at first glance like a classic example. It possesses a bright central core and not one but 2 distinct rings. But when astronomers pointed their spectral instruments at this cosmic bullseye, they discovered something profoundly bizarre. The stars in the outer ring were not the brilliant blue newborns we would expect. They were significantly older than the stars in the inner ring. This is the equivalent of finding a fossilized tree where the outermost growth rings are younger than the inner ones. It violates the fundamental sequence of events we thought governed these structures. This age inversion creates a direct challenge to the standard single collision model. In that simple picture, a smaller galaxy punches through the center of a larger disk, sending a density wave rippling outward. This wave triggers star formation first at the outer edge, creating the ring. The outer ring is therefore always the youngest feature. For LEDA 1000714, this logic is completely appended. The existence of an older outer ring forces astronomers to consider a far more complex and drawn-out history. one involving multiple galactic interactions over billions of years. This isn't a snapshot of a single cataclysm. It's a palimpsest, a cosmic document where one violent story has been written over the faint traces of an earlier one. The most compelling explanation for this strange chronology is a multi-stage merger. Imagine the initial event billions of years ago. The primary galaxy may have undergone a collision that formed the first outer ring. This ring would have blazed with blue light for a time before its massive stars died off, leaving behind a population of longer-lived, older and redder stars. The galaxy would have then entered a relatively quiet phase, with this faint, aging ring slowly expanding. Then, much later, a second, more recent interaction occurred. Perhaps another small galaxy ventured close, or the same companion galaxy made another pass. This new encounter sent a second density wave through the system, but this wave propagated through a galaxy that had already been fundamentally altered. The gas distribution was different, and the gravitational landscape had changed. This second wave triggered a new burst of star formation, not at the new outer edge, but further inward, creating the younger, bluer inner ring we see today. In this scenario, the galaxy is a chronicle of two distinct epochs of violence, separated by a long cosmic interlude. An alternative and even more intriguing possibility involves a phenomenon known as resonance. Instead of requiring two separate collisions, a single, complex merger might have set up multiple resonant patterns within the galaxy's disk. The gravitational forces from the merging galaxies could have created stable orbits at two different radii, one far out and one closer in where gas naturally accumulates. It's possible that the gas at the outer resonance radius collapsed and formed stars first, for reasons related to the precise timing of the interaction or the initial distribution of gas. Later, as the system settled, star formation ignited at the inner resonance, resulting in the observed age difference. This would mean that both rings are related to the same primordial event, but their star formation was triggered in a sequence that defies our simple outward wave model, governed by the intricate music of gravitational forces. Studying a galaxy like letter 1000714 is like being a cosmic archaeologist. The different rings are layers of a dig site, each holding artifacts from a different era. By meticulously dating the stars in each ring, using their color and brightness to estimate their age, astronomers can piece together a timeline of the galaxy's tumultuous past. The peculiar age structure makes this galaxy an invaluable test case for sophisticated computer simulations. Can models that simulate multiple mergers or complex resonances successfully reproduce this inverted ring structure? When scientists run these digital experiments, they are not just creating a pretty animation. They are testing the very physics of galactic interactions against one of the most awkward and challenging observations nature has provided. The existence of such an object reminds us that galaxies are not static portraits but dynamic entities with long and often repetitive histories of violence and assimilation. While the simple, elegant ring galaxy provides a clean model for understanding basic principles, it is the oddballs, the outliers like letter 1000714 that truly push the boundaries of our knowledge. They force us to consider that the universe is far more creative and complicated than our simplest stories, capable of writing its history in loops of starlight that challenge our perception of time itself. So far, our exploration of ring galaxies has been a story told primarily in the light our eyes can see, the brilliant blue of young stars and the golden glow of ancient ones. But to truly understand these cosmic wonders, we must learn to see the universe in a radically different way. Every ring galaxy is a multi-layered entity, and each layer reveals its secrets in a specific type of light, from the long, gentle waves of radio to the short, violent bursts of X-rays. By combining these different views, astronomers don't just get a prettier picture, they assemble a complete, three-dimensional understanding of the galaxy's anatomy, physics, and history. Let's start with the radio universe. To our eyes, the space between the stars in a ring galaxy might look like an empty black void. But when we tune our telescopes to the specific radio wavelength emitted by neutral hydrogen gas, something astonishing happens. The entire ring, and often the space between the ring and the core, lights up with a faint ethereal glow. This is the reservoir of raw material, the cold hydrogen fuel that has yet to collapse into stars. Radio observations map the distribution of this primordial gas, showing us the exact pathway of the density wave. We can see the shock front itself as a compressed ridge of hydrogen, a wall of gas that has been piled up by the gravitational tsunami. Even more telling, radio telescopes often reveal long, faint streams of hydrogen stretching far beyond the visible ring, the tidal tails left over from the collision, pointing like ghostly arrows back toward the escaped intruder galaxy. This radio view reveals the skeleton of the system, the unseen mass of fuel that holds the key to its past and future. Now switch to the infrared. If radio waves show us the cold gas, infrared light pierces through the veils of cosmic dust. Dust grains spewed out by previous generations of stars are excellent at blocking visible light but glow brightly when warmed by the heat of newborn stars. An infrared view of a ring galaxy is like using night vision goggles to see through smoke. The brilliant blue ring we see in visible light often fractures into even more spectacular, blazing knots of infrared emission. These are the densest, most obscured stellar nurseries, where stars are forming in such thick cocoons of dust that they are completely hidden from optical telescopes. The infrared reveals the true, ferocious intensity of the star-forming frenzy, often showing that it is even more concentrated and vigorous than the visible image suggests. Furthermore, the infrared can peer into the very heart of the quiet central core, detecting the faint glow of cool, older stars that are otherwise lost in the glare, giving us a more accurate census of the galaxy's ancient stellar population. Then there is the X-ray view, which unveils the most violent and energetic processes at work. When we observe a ring galaxy with an X-ray telescope, the calm, structured beauty of the optical image gives way to a scene of cosmic violence. The entire ring can be dotted with brilliant X-ray sources. Many of these are the remnants of massive stars that have already lived their short lives and exploded as supernova. The expanding shockwaves from these explosions heat the surrounding gas to millions of degrees, causing it to glow in X-rays. Other bright spots could be binary star systems where a black hole or neutron star is actively siphoning material from a companion, heating it to incredible temperatures in the process. Perhaps most importantly, the very center of the galaxy, which might appear quiet in visible light, could host a brilliant X-ray source, the signature of the central supermassive black hole actively accreting material, awakened from its slumber by the same collision that triggered the ring. The X-ray vision shows us the galaxy's power plants and its graveyards, the sites of immense energy release that are shaping its evolution. This multi-wavelength approach is not just a neat trick, it is the cornerstone of modern astrophysics. A single wavelength tells only part of the story. The visible light shows us the present-day stars, the radio reveals the future fuel for stars, the infrared exposes the hidden sites of current birth. And the X-rays chronicle the deaths of stars and the activity of black holes. By layering these views together, astronomers can track the complete cycle of matter and energy within the ring galaxy. They can see how the cold gas from the radio map is compressed into the dust-shrouded nurseries of the infrared image, which then produce the brilliant stars of the optical view, which ultimately die and create the violent X-ray remnants that enrich the galaxy with heavy elements. It is through this symphony of light across the entire electromagnetic spectrum that a ring galaxy transforms from a beautiful picture into a dynamic, evolving ecosystem, whose full story can only be read by learning to see in all the colors of the cosmic rainbow. After exploring these myriad wonders, from counter-rotating rings to binary pairs, a fundamental and puzzling question naturally arises. If the processes that create ring galaxies are governed by universal laws of physics, why are these stunning structures so exceptionally rare in the cosmos? Given the countless galaxies constantly interacting in the vastness of space, we might expect to see celestial wedding bands adorning every corner of the universe. Their scarcity is not an illusion. It is a direct consequence of the incredibly precise and unforgiving set of conditions required for a perfect ring to emerge from the chaos of a galactic collision. The primary challenge lies in the geometry of the impact itself. For a classic, symmetric ring like Hoag's object or the Cartwheel Galaxy to form, the collision must be a near-perfect bullseye. A smaller galaxy must pass almost directly through the center of a larger disk galaxy's rotational axis. This is a cosmic shot of astonishing accuracy. Now consider the alternative. The vast majority of galactic encounters are not head-on collisions. They are glancing blows, near misses, or slow, grazing mergers. When two galaxies interact at an angle, their gravitational forces don't create a clean, expanding ripple. Instead, they pull and twist each other, stretching out long tidal tails of stars and gas, warping their disks and creating the beautiful but messy grand design spirals and irregular galaxies we commonly observe. A direct hit is the exception, not the rule, in the random, chaotic dance of galaxies. Beyond the precise angle, the nature of the galaxies involved is equally critical. The target galaxy needs to be a relatively thin, ordered disk, a spiral galaxy rich with gas. If it's a puffy elliptical galaxy, which is essentially a spherical swarm of stars with random orbits, a collision will just stir the swarm without producing any coherent structure. The intruder, in turn, must be of an appropriate size. If it's too large and massive, an equal mass merger will completely destroy the disk of the larger galaxy, resulting in a chaotic mess that eventually forms a new elliptical galaxy. If the intruder is too small, its gravitational kick will be insufficient to trigger a galaxy-wide density wave. It might only create a small warp or a localized burst of star formation, leaving the main disk largely intact. The ideal intruder is a gas-rich dwarf galaxy massive enough to make an impact, but not so large as to cause total annihilation. The timing of the ring's visibility adds another layer to its rarity. A ring galaxy is not a permanent phase in a galaxy's life. It is a brilliant but fleeting spectacle. The iconic blue ring of young stars shines for a relatively short cosmic timescale, perhaps only a few 100 million years. After that, the most massive stars explode as supernova, and the ring's color fades to yellow and then red as the stellar population ages. The structure itself also evolves, becoming distorted by gravitational instabilities or disrupted by subsequent interactions. What we are able to observe is therefore a very narrow window in a galaxy's multi-billion-year history. We are catching these cosmic fireflies in the brief moment their lights are on, while for the vast majority of their lives they appear as far more ordinary objects. Furthermore, the environment plays a decisive role. While galaxy clusters have a high rate of interactions, making them potential ring factories, they are also incredibly hostile environments. The same tidal forces from neighboring galaxies that might help create a ring can also quickly tear it apart. A ring galaxy born in a dense cluster may have a lifespan cut short by gravitational harassment, its delicate structure shredded before we ever get a chance to observe it in its prime. The most pristine rings we see might therefore be those that formed in relative isolation, where they could evolve without constant disturbance. But these isolated regions also have a much lower probability of a galactic collision occurring in the first place. This creates a cosmic catch-22. The best places to make rings are also the worst places for them to survive. This rarity is what makes each ring galaxy we discover so scientifically precious. They are not just beautiful accidents, they are the outcomes of a cosmic lottery where the odds are stacked against them. Their existence confirms that the physics of density waves and gravitational interactions works exactly as our models predict, but only under the most ideal and unlikely circumstances. Every perfect ring is a testament to a moment of precise violence in an otherwise random universe, a fleeting alignment of mass, momentum, and geometry that transforms a routine collision into a temporary masterpiece of celestial architecture. But within that brilliant blue firestorm of a ring galaxy's youthful stars, there exists a far more subtle and serene kind of cosmic light show, one that speaks not of birth but of a graceful and final farewell. Scattered among the massive, short-lived O and B stars are countless smaller, sun-like stars, living out their lives over billions of years. And when these stars reach the end of their long journey, they do not go out with the cataclysmic bang of a supernova. Instead, they offer up a final, beautiful gift to the universe, a planetary nebula. These are not planets, as the name might suggest from its historical origins, but vast, intricate shells of glowing gas gently ejected from the dying star at its center. In a ring galaxy, these ghostly, often greenish-hued nebulae become incredibly valuable scientific tools, acting as cosmic census takers for the galaxy's older, hidden stellar population. The formation of a planetary nebula is a slow, elegant process. A star similar to our Sun spends most of its life calmly fusing hydrogen in its core. But when it exhausts this fuel, it undergoes a profound transformation. The star swells into a red giant, becoming unstable. In its final throes, it pulsates, gently pushing its outer layers out into space in a series of slow cosmic winds. The hot, exposed core of the star, now a white dwarf, bathes this expanding shell of gas in intense ultraviolet radiation, causing it to fluoresce with a characteristic glow. Each planetary nebula is therefore a temporary monument to a single, dying star, visible for only a few tens of thousands of years, a mere blink in cosmic time. Their brilliance comes not from their own power, but from the light of the stellar ember at their heart. In a chaotic environment like a spiral galaxy, pinpointing the exact stellar population that produced a specific planetary nebula can be difficult. But in a ring galaxy, we are handed a remarkable advantage, because the ring itself was formed in a single, recent burst of star formation. We know that the vast majority of stars within it were born at roughly the same time. This turns the ring into a controlled laboratory for stellar evolution. The presence of planetary nebulae within the ring tells us something crucial, that the burst of star formation which created the ring was not exclusively limited to massive stars. It also produced a significant population of intermediate and low-mass stars, the kind that end their lives as planetary nebulae. Their very existence confirms that the ring contains a full spectrum of stellar masses, from the Titans to the Sun-like stars. The true power of these objects, however, lies in their distribution. While the brilliant blue light of the ring is dominated by the youngest, most massive stars, the planetary nebulae are not confined to these brightest regions. In fact, their distribution can be radically different. Astronomers use specialized filters on their telescopes to isolate the specific wavelength of light emitted by ionized oxygen, a hallmark of planetary nebulae. When they create maps of a ring galaxy using this technique, they often find these nebulae scattered not just throughout the blue ring, but also in the seemingly empty gap between the ring and the core, and even within the central core itself. This distribution is a direct map of the older stellar population that is otherwise invisible amidst the glare of the young stars. This provides a profound insight into the galaxy's history that is unavailable through any other means. The presence of planetary nebulae in the gap is particularly telling. It indicates that this apparently empty region is not truly empty. It is populated by a diffuse background of older stars that were part of the original galactic disk before the collision. These are the stars that were not swept up by the density wave, left behind like a ghostly remnant of the galaxy that once was. By counting the number of planetary nebulae in the gap versus the ring, astronomers can estimate what fraction of the original disk stellar population was involved in the ring-forming event. Similarly, finding them in the central core helps date the stars there, confirming that they are indeed the ancient relics of the progenitor galaxy. Each planetary nebula is a beacon, illuminating the location of a single ancient star and collectively tracing the skeletal structure of the galaxy's past. But all the violent drama of the collision and the brilliant aftermath of star formation unfolds within an invisible arena, one that was built long before the first stars of the galaxy ever ignited. We have mentioned the dark matter halo in passing, but to truly understand the fate of a ring galaxy, we must venture deeper into the nature of this mysterious scaffolding. It's not enough to know the halo is there. We must ask a more specific question. What is its shape? Is it a perfect sphere, a flattened disk, or a stretched-out football? This seemingly abstract property of the invisible majority of a galaxy's mass turns out to be one of the most critical factors determining whether a beautiful ring can form at all and how long it can survive. Think of it this way: the visible stars and gas of a galaxy are like a chandelier suspended from an unseen ceiling. The stability and motion of that chandelier depend entirely on the structure of the ceiling beams holding it up. If the beams are arranged in a symmetric dome, the chandelier can swing smoothly. But if the beams are irregular or slanted, the chandelier's motion will be awkward and unstable. For a ring galaxy, the dark matter halo is that ceiling. Its shape dictates the gravitational landscape through which the ring must orbit. A spherical halo provides a uniform, symmetric gravitational field that helps maintain the ring's perfect circular form. But if the halo is significantly flattened, like a hamburger bun, or elongated, like a cigar, the gravitational forces acting on the ring become uneven, pulling it out of shape and threatening its very existence. This is where supercomputer simulations become our most powerful tool, allowing us to run controlled experiments that would be impossible in the real universe. Astronomers create virtual galaxies with identical visible properties, the same mass of gas, the same disk structure, but THEY Chinese letter them dark matter halos of different shapes. They then simulate the same bullseye collision with a small intruder galaxy and watch what happens. The results are dramatic. In a simulation with a spherical halo, the density wave propagates outward cleanly, creating a near-perfect, stable ring that can persist for hundreds of millions of years. The symmetric gravity supports the ring's circular orbit, allowing it to expand gracefully. Now, run the same simulation with a highly flattened or oblate halo. The outcome is strikingly different. The gravitational field is no longer the same in all directions. It's stronger along the plane of the flattening. This asymmetry disrupts the clean propagation of the density wave. The ring that forms is often warped or elliptical from the very beginning. Even more critically, the ring's orbit becomes unstable. It experiences a gravitational torque that causes it to wobble and precess, much like a spinning top slowing down. This wobbling motion increases the ring's contact with the uneven gravitational field, which rapidly saps its orbital energy through dynamical friction. In these simulations, the ring doesn't just fade, it quickly breaks apart and falls inward toward the galactic center, its beautiful structure dissolved long before its time. The opposite shape, a prolate or football-shaped halo, presents its own unique challenges. In this configuration, the elongated gravity tends to funnel material along its long axis. When the collision sends a wave outward, the force of the halo can squash the ring, preventing it from achieving a large, symmetric diameter. The ring may form, but it will be smaller, tighter, and under immense gravitational stress. Simulations show that such rings are highly prone to fragmentation, collapsing into clumps of stars rather than maintaining a coherent loop. The halo's shape essentially strangles the ring in its infancy, preventing it from ever reaching the spectacular proportions we see in objects like the Cartwheel Galaxy. These simulations do more than just explain why some rings are perfect and others are misshapen. They provide a way to indirectly measure the shape of a real galaxy's dark matter halo. By carefully observing the precise form and motion of a ring, noting any warps, measuring its expansion rate, and tracking any signs of precession, astronomers can compare it to the library of simulation results. If a ring is perfectly circular and stable, it strongly suggests a spherical halo. If it shows a distinct warp and is decaying rapidly, it points toward a flattened halo. The ring itself becomes a diagnostic tool, a visible tracer moving within an invisible gravitational field, revealing the hidden architecture that governs its destiny. This turns the ring galaxy from a passive subject of beauty into an active probe for one of the greatest mysteries in cosmology, showing us that the most profound secrets of the universe can be hidden in the graceful geometry of a circle of stars. Now, let's turn our gaze from the grand physics of galactic collisions to a much more intimate question, one that touches on our own place in the cosmos. We've marveled at the ring galaxy as a cosmic engine of creation and destruction, but could it also be an engine for life? Is it possible that within these magnificent structures, on worlds orbiting stars in either the brilliant ring or the quiet core, conditions might arise that are suitable for biology? This is a deeply speculative but profoundly fascinating line of inquiry, one that forces us to weigh the violent beauty of the ring against the serene patience of the core in the universal search for habitable real estate. First, consider the ring itself, a region of intense and relentless activity. This is the stellar nursery, blazing with the light of millions of young, massive stars. For a planet forming here, the environment is one of extreme privilege and extreme peril. On the positive side, these massive stars are prolific factories for the heavy elements essential for life. Carbon, oxygen, nitrogen, and iron are forged in their cores and scattered throughout the region by supernova explosions. Any planetary system taking shape in the ring would be born from gas and dust already richly seeded with these fundamental building blocks. The very material for rocky planets and the complex chemistry of life would be abundant from the start. However, the same stellar giants that provide these elements also unleash a torrent of harmful radiation. O and B-type stars flood their surroundings with intense ultraviolet and X-ray radiation, a constant barrage that could easily strip away the atmosphere of a nascent Earth-like planet and sterilize its surface. Furthermore, the likelihood of a nearby supernova explosion within the first few tens of millions of years is incredibly high. Such an event, occurring even a few dozen light-years away, could bathe a planet in enough radiation to cause mass extinctions or worse. The ring, for all its creative power, is a chaotic and dangerous neighborhood where planetary survival requires either incredible luck or a very rapid emergence of life in the brief window of relative calm between a planet's formation and the next catastrophic stellar explosion. This leads us to the quieter realms of the galaxy, the ancient central core. Here, the stellar population is overwhelmingly composed of older, smaller, more stable stars, yellow and red dwarfs similar to our Sun or smaller. The radiation environment is far gentler without the constant threat of a nearby supergiant going supernova. A planet orbiting one of these stars would enjoy a much more stable and predictable long-term climate, a seeming prerequisite for the slow, gradual evolution of complex life. The core, in this view, appears to be a galactic sanctuary, a quiet retirement community where life could evolve over billions of years without constant cosmic interruption. Yet, this apparent tranquility may come at a steep cost. The very violence that makes the ring dangerous is also what enriches it. The core, having been largely stripped of its gas during the collision that formed the ring, is a region where star formation died long ago. This means the planetary systems around its ancient stars would have formed from material that was chemically less evolved than the later generations in the ring. They might be deficient in the heavier elements necessary for terrestrial planets and the complex chemistry of life as we know it. A planet in the core could be a stable, peaceful world, but it might also be a barren rock, lacking the rich elemental diversity that acted as a catalyst for biology on Earth. It's a trade-off between safety and resource abundance. Perhaps the most intriguing possibility lies not strictly in the ring or the core, but in the transition zone between them. Imagine a solar system that formed in the ring during its initial burst, but whose star, over hundreds of millions of years, migrated slightly inward, away from the most intense radiation. Its planets would have benefited from the ring's rich metallicity during their formation, but then been carried to a more sheltered orbital distance. Alternatively, consider a star that formed just after the main wave passed, from gas that had been enriched by the first supernova, but was now located in a slightly quieter suburb of the ring. In these Goldilocks zones of the ring galaxy, not too close to the stellar inferno, yet not too far from the source of materials, the conditions for habitability might be just right. Ultimately, the question of life in a ring galaxy expands our perspective on astrobiology. It teaches us that a galaxy's history is inextricably linked to its potential for biology. A ring galaxy presents not one, but two starkly different paths for life, a fast, intense, and risky path in the brilliant but short-lived ring, and a slow, patient, and potentially resource-poor path in the ancient core. Which path is more likely to lead to life remains one of the great open questions. It reminds us that habitability is not just about a single star and its planet. It's about the entire galactic environment, shaped by events of cataclysmic violence that can, paradoxically, create both the conditions for life's emergence and the greatest threats to its survival. Now, let's experience a ring galaxy in a way you never have before. Not with your eyes, but with your ears. We are about to translate the silent, majestic rotation of one of these cosmic structures into sound, a process known as sonification. Imagine taking the precise data from a telescope, the orbital speeds of stars at different distances from the galactic center, and mapping it onto a musical scale. The slow, ponderous drift of a gas cloud at the very edge of the ring might become a deep, resonant cello note, while the frantic, whipping motion of a star cluster closer to the core escalates into a high, sharp violin tone. The result is not music in the traditional sense, but a data symphony, a direct auditory representation of the galaxy's gravitational dance. This is more than a novelty. It's a powerful analytical tool that allows scientists, and now us, to perceive patterns in the data that might be hidden in a graph or an image. Here is a sample of such a sonification. As you listen, you'll notice the sound begins with a low, steady hum, representing the more sedate outer regions of the ring. Then, as the data scan moves inward, the pitch rises steadily but not smoothly. You might hear a distinct wobble, a slight warble in the tone, or even a sudden drop before the pitch climbs again. These auditory anomalies are crucial. In a visual graph, a small kink in a rotation curve might be easy to overlook, buried among dozens of other data points. But to the human ear, which is exquisitely sensitive to changes in frequency and rhythm, that same kink becomes an obvious dissonance, a clear signal that something unexpected is happening in the galaxy's motion. This auditory irregularity could correspond to a region where the gravitational pull is weaker or stronger than predicted, potentially pointing to a clump of dark matter, a past minor merger, or an area of intense magnetic pressure affecting the gas flow. The true power of sonification lies in its ability to tap into the human brain's innate talent for pattern recognition within sound. We are wired to detect a wrong note in a melody or the distinct rhythm of a specific engine noise. Astronomers can use this ability to literally listen to a galaxy's rotation for signs of instability or unique structure. For instance, a perfectly smooth, linear rise in pitch would suggest a galaxy with a very standard and evenly distributed mass. But if the sonification of a ring galaxy produces a sound that is lumpy, with stutters and jumps, it immediately suggests that the mass distribution is not smooth, that there are hidden densities and voids within the dark matter halo that are tugging on the visible stars in complex ways. It turns abstract data into an experience, allowing for an intuitive grasp of the galaxy's dynamic state. This technique also provides a remarkable bridge to accessibility, making the wonders of astrophysics available to a wider audience, including those who are blind or have low vision. A complex graph is inherently visual, but a sonified dataset can be explored and understood through hearing alone, opening up the field to new minds and perspectives. Furthermore, by comparing the sound of a ring galaxy to that of a normal spiral or an elliptical galaxy, we can hear the profound differences in their dynamics. The resonant, rising chord of a ring galaxy, born from a clean, expanding wave, has a very different character from the more chaotic, discordant sounds of a merging system. In this way, sonification does not replace traditional analysis. It complements it, adding a new dimension to our perception and offering a unique pathway to discovery, where listening to the cosmos can be just as illuminating as looking at it. But to truly grasp the strange nature of these galaxies, we must venture into the most elusive dimension of all, the realm of the invisible. We've discussed how a collision rearranges the visible stars and gas, but what about the ghost that holds the entire system together? What happens to the dark matter? Theoretical models are now suggesting something truly mind-bending. The same cataclysm that forges the brilliant ring of stars might also, for a fleeting cosmic moment, imprint a similar ring onto the galaxy's invisible dark matter halo itself. We could be looking at a celestial structure where the luminous ring we see is just the visible tip of a much larger, darker iceberg. The idea hinges on a key difference between dark matter and normal matter. The gas and dust that make up the visible ring are what physicists call collisional. When gas clouds slam into each other, they compress, heat up, and create friction, which is exactly how the density wave triggers star formation. Dark matter, as far as we understand it, is almost entirely collisionless. The particles that make up the halo pass right through each other and through normal matter without interacting, feeling only the pull of gravity. So, when the intruder galaxy makes its bullseye pass, it doesn't create a shock wave in the dark matter in the same way it does in the gas. Instead, its gravity tugs on the dark matter particles, setting them oscillating. Think of it not like a pebble creating a ripple in a pond, but like a clapper striking a bell. The entire dark matter halo begins to ring or vibrate. As these gravitational vibrations propagate through the halo, they can lead to a phenomenon known as a caustic, a region where the orbits of the dark matter particles pile up, creating a temporary shell-like density enhancement. This would be a genuine ring of dark matter, a subtle, invisible echo of the visible ring of stars, likely on a much larger scale. It's a fascinating prediction. The same event creates two concentric rings, one of brilliant light and one of pure gravity, one made of stuff we understand and one made of stuff we are still desperately trying to identify. So, how could we possibly detect such a phantom structure? We can't see it, but we can feel its gravitational influence. This is where the phenomenon of gravitational lensing becomes our most powerful tool. As we discussed earlier, a massive object warps spacetime, bending the path of light from background galaxies. A smooth, spherical dark matter halo would create a relatively simple lensing effect. But a halo that has been disturbed, one that contains a dense, ring-like enhancement, would create a far more complex and distinctive signature. The gravity of the dark matter ring would act as an additional lens, potentially creating multiple, distorted images of a single background galaxy that are arranged in a subtle circular pattern, a ghostly fingerprint of the ring's presence. The challenge, of course, is immense. The signal would be incredibly faint, requiring exquisitely precise measurements from the most powerful telescopes. Astronomers would need to observe a ring galaxy that is perfectly aligned with a more distant galaxy to use as a background light source. Then, by meticulously mapping the distortions in that background light, they could work backwards to model the mass distribution of the foreground galaxy. If the simplest model, a smooth halo plus the visible ring of stars, fails to explain the observed lensing pattern, but a model that includes a temporary dark matter ring provides a perfect fit, it would be compelling, albeit indirect, evidence for this extraordinary phenomenon. Detecting such a dark matter ring would be a monumental achievement. It would provide a unique laboratory for studying the properties of dark matter itself. For instance, if the ring is sharp and well-defined, it would suggest that dark matter is cold, meaning its particles move relatively slowly, allowing them to clump together neatly. If the ring is diffuse or washes out quickly, it might hint at warm, dark matter where faster-moving particles resist such clean clustering. This single observation could help narrow down the vast field of candidates for what dark matter actually is. The beautiful, luminous ring of a galaxy like Hoag's object may therefore be more than just a cosmic wonder. It could be the key that helps us finally illuminate the dark heart of the universe. Yet long before astronomers ever trained their telescopes on these celestial wonders, the human imagination had already been captivated by the symbol of the perfect circle. The ring galaxy, in many ways, represents the ultimate fulfillment of that ancient archetype on a cosmic scale. And it's no surprise that once real images of objects like Hoag's object began to circulate, they quickly found a home in the realm of science fiction. Filmmakers, authors, and video game designers saw in these structures a visual shorthand for the truly alien, the profoundly advanced, and the gateway to realms beyond our understanding. Let's take a journey through some of these fictional portrayals and see how they stack up against the scientific reality. One of the most common tropes is the ring galaxy as the ultimate achievement of a hyper-advanced civilization. This is the concept of a Dyson sphere, but taken to a galactic level. In such stories, a species so powerful that they can rearrange the very stars themselves builds a ring as a habitat, a power source, or a defensive fortification. The sheer artificial perfection of a galaxy like Hoag's object makes this leap of logic almost irresistible. The fiction presents the ring as a stable, permanent structure, meticulously engineered and controlled. The scientific reality, of course, is far more violent and temporary. Rather than a feat of engineering, the ring is a scar, a natural byproduct of a catastrophic collision that will last for only a few 100 million years before fading away. The fictional version speaks to our desire for order and mastery over the cosmos, while the real thing is a testament to the chaotic, destructive, and yet beautifully creative forces of nature that are entirely beyond any control. Another popular theme is the ring galaxy as a cosmic portal or a gateway to another universe. Its unique geometry, a hole punched through the fabric of a galaxy, naturally suggests a passageway. In various stories, venturing into the center of a ring galaxy might allow for faster-than-light travel, time travel, or communication with other dimensions. The empty gap between the ring and the core becomes a mysterious void brimming with unknown energy. This is a fascinating contrast to the scientific understanding. In reality, that gap is not empty. It's filled with a diffuse population of older stars from the original galactic disk and, we believe, a vast sphere of dark matter. It's not a gateway, but rather the preserved heart of the galaxy that was. The fictional portal represents a yearning for connection and exploration beyond our limits, while the actual ring galaxy offers a connection to the past, a window into the galaxy's own history, not a door to another realm. Perhaps the most poignant comparison lies in the way fiction and science both use the ring galaxy to explore themes of cosmic cycles and rebirth. In several epic space operas, a ring galaxy is depicted as the site of a celestial resurrection, a place where a dead universe is reborn or where a dying civilization is given a second chance. This metaphor is strikingly aligned with the scientific narrative. The real ring galaxy is a story of rebirth. A mature, settled spiral galaxy is effectively destroyed in a collision, but from that destruction springs a new, vibrant structure, the brilliant blue ring of newborn stars. The galaxy is reborn from its own ashes, its identity transformed. The fiction focuses on a spiritual or conscious rebirth, while the science reveals a physical, structural one. Yet both interpretations recognize the ring as a powerful symbol of destruction and renewal on the grandest possible scale. These fictional depictions, while often taking great liberties with physics, serve a valuable purpose. They ignite public fascination and provide a narrative gateway that leads people to the real science. Someone who first encounters a ring galaxy in a video game might be inspired to look up images from the Hubble Space Telescope, and in doing so, they learn about galactic collisions, density waves, and stellar evolution. The fiction acts as a bridge, transforming an abstract astronomical concept into a tangible and exciting idea. It reminds us that science and storytelling are not enemies. They are two different ways of seeking meaning in the cosmos. One uses equations and telescopes to understand how the universe works, while the other uses symbols and narratives to explore what it means for us. The ring galaxy, in its perfect, mysterious symmetry, provides fertile ground for both, a celestial canvas upon which we project our deepest questions about creation, destiny, and our place in the vast starry night. For nearly a century, astronomers have relied on a powerful organizational tool to bring order to the vast diversity of galaxies, the Hubble sequence. Picture this iconic diagram, often called the Hubble tuning fork. On one side, you have the elegant spiral galaxies with their curved arms winding out from a bright central bulge. These are further divided into barred and unbarred varieties. On the other side of the fork, you find the smooth, featureless elliptical galaxies, ranging from nearly spherical to highly elongated. And right at the junction, the lenticular galaxies act as a bridge, possessing a disk but no spiral arms. This classification system has been enormously successful, providing a framework to understand how galaxies might evolve and relate to one another. But where exactly does a perfect circle of stars like Hoag's object fit on this chart? The startling answer is that it doesn't. A ring galaxy is a square peg that simply will not fit into the round holes of the Hubble sequence, and its very existence challenges the quiet, evolutionary assumptions the tuning fork implies. The core of the problem lies in the fundamental difference between structure and origin. The Hubble sequence is primarily a morphological system. It classifies galaxies based on what they look like now. A spiral galaxy is defined by its spiral arms, an elliptical by its smooth, amorphous shape. If you were to take a simple photographic atlas and try to slot a ring galaxy into this scheme, you might be tempted to call it a peculiar spiral or a special kind of lenticular. But this would be a profound misclassification, because the reason a ring galaxy looks the way it does is entirely different from the reasons a spiral or elliptical has its form. A grand design spiral's arms are thought to be sustained by density waves propagating through a stable, rotating disk over billions of years. An elliptical galaxy's shape is the result of a long history of mergers that have randomized stellar orbits. A ring galaxy, by contrast, is the product of a single, recent and catastrophic event, a galactic bullseye collision. Its structure is not a stable, long-term phase of evolution. It is a temporary, dramatic and transient state. This distinction reveals a critical limitation of the Hubble sequence. It implicitly assumes a universe where galaxies evolve slowly and peacefully through internal processes or gentle interactions. It doesn't have a category for objects whose entire identity is shaped by a brief, violent, and external shock. Placing a ring galaxy on the tuning fork would be like trying to classify a rainbow alongside different types of clouds. Both are atmospheric phenomena, but one is a stable structure formed by slow processes, while the other is a fleeting effect caused by the specific, momentary interaction of light and water. The ring galaxy is the rainbow of the extragalactic world, a beautiful consequence of a specific event, not a permanent class of object in a slow evolutionary chain. Some astronomers have attempted to force ring galaxies into the existing scheme by labeling them as peculiar galaxies, denoted by the suffix P. You might see a ring galaxy referred to as a S0P galaxy, for example, meaning a peculiar lenticular. But this feels like an admission of defeat, a way of saying, this object breaks our system, so we'll just mark it as weird. It doesn't capture the essence of what a ring galaxy is. A more accurate approach is to think of galactic classification as having two separate axes. One axis is the traditional Hubble sequence, describing the quiescent forms of galaxies, how they appear when left to evolve in isolation or with only minor disturbances. The other axis is for transient or event-driven forms. On this second axis, you would find ring galaxies, along with other collision-induced structures like tidal tail galaxies and polar ring galaxies. These are not endpoints on an evolutionary path. They are dramatic, short-lived chapters in a galaxy's life story. Recognizing ring galaxies as a distinct category outside the Hubble sequence has profound implications for how we understand galactic evolution. It forces us to acknowledge that a galaxy's history is not just a slow, deterministic march along the tuning fork from spiral to elliptical. Instead, a galaxy's life can be completely upended by a random, catastrophic event that reshapes it into something entirely new for a few 100 million years. A spiral galaxy can be transformed into a ring not by a slow internal process, but by a sudden external impact. And after the ring fades, that galaxy will not return to being a spiral. It will likely evolve into a lenticular or an elliptical. The ring phase is a disruptive, transformative event that can shunt a galaxy from one branch of the Hubble sequence to another. Therefore, ring galaxies are not just curiosities. They are vital evidence for a more dynamic and violent view of the universe. They teach us that the Hubble sequence, for all its utility, is merely a snapshot of the most common, stable configurations. It is a field guide to the adult forms of galaxies. But to understand the entire life cycle, including the rare, violent, and spectacular births, we need to look to the outliers, the peculiar objects that defy easy categorization. The perfect ring floating in space is a testament to the fact that sometimes the most important stories are the ones that don't fit neatly into our boxes, reminding us that the cosmos is far more creative and disruptive than any simple diagram can capture. The story of ring galaxies, with all their intricate mysteries, is on the verge of a revolution, not because of a single new theory, but because of an impending avalanche of pure data. For decades, these celestial oddities have been rare treasures, painstakingly discovered one by one, their study limited to a few dozen well-known examples. But our perspective is about to shift from examining individual jewels to surveying entire mountain ranges. The next generation of astronomical observatories, led by projects like the Vera C. Rubin Observatory, will not merely add to our catalog. They will transform ring galaxies from fascinating curiosities into a powerful statistical population, allowing us to move from asking, "How did this one form?" to answering, "What are the universal laws that govern them all?" Scheduled to begin its ambitious 10-year legacy survey of space and time, the Vera C. Rubin Observatory will fundamentally change the scale of discovery. Its massive mirror and enormous camera will scan the entire visible southern sky every few nights, not just once, but over and over again. This repeated all-sky coverage is the key. It means that instead of relying on chance alignments or targeted studies, we will have a continuous cinematic view of the universe. The observatory is expected to detect tens of billions of celestial objects, and within that unimaginably vast dataset, astronomers predict we will find not dozens, not hundreds, but potentially thousands of ring galaxies. This leap in quantity is not just about having more examples to look at. It's about unlocking an entirely new branch of science, statistical astrophysics. With a sample size of thousands, we can finally begin to answer questions that have been purely speculative until now. For instance, what is the true lifetime of a ring galaxy's brilliant blue phase? By finding rings at all different stages of evolution, from the freshly ignited, searingly blue newborns to the faded, reddish remnants, and by knowing how common each type is, we can construct a reliable timeline of their life cycle. If we find very few middle-aged yellow rings compared to young blue ones, it would suggest that the phase is short-lived, perhaps because supernova feedback quickly shuts down star formation. If we find many old red rings, it would imply these structures can persist in a quiet state for much longer than our current models predict. The Rubin data will allow us to plot these galaxies on a chart and see the real shape of their existence, turning qualitative ideas into quantitative facts. This statistical power will also resolve long-standing debates about their formation. Is the classic bullseye collision the only path, or are rings formed through internal resonances just as common? By analyzing thousands of images, astronomers will be able to measure the properties of the host galaxies. If most ring galaxies are found in isolated environments, it would support the resonant theory, as there would be no obvious intruder to blame. But if a significant majority are found in galaxy groups or clusters with smaller companion galaxies nearby, it would be powerful evidence for the collisional model. We could even correlate the ring's perfection with the local density of galaxies, testing how often these delicate structures are disrupted by their neighbors. The data will allow us to move beyond the unique stories of objects like the Cartwheel Galaxy and understand the dominant narrative of ring formation across the cosmos. Furthermore, the Rubin Observatory's time domain aspect, its ability to see how the sky changes night after night, will turn these static structures into dynamic laboratories. It will automatically discover supernova within these rings by the thousands. This will provide an unprecedented dataset to test our models of stellar evolution in a controlled environment. We will see if the most massive stars in the rings truly do explode first, as predicted, and we can use this sequence to calibrate our understanding of how stars of different masses live and die. The light echoes from these supernovae, which we currently study with painstaking effort on a case-by-case basis, could be detected and tracked automatically for hundreds of events, allowing us to map the three-dimensional structure of ring after ring with robotic efficiency. The discovery potential doesn't end with Rubin. When combined with the deep, infrared eyes of the James Webb Space Telescope and the precision astrometry of the European Space Agency's Gaia mission, we will enter a golden age of ring galaxy science. Webb can follow up on Rubin's discoveries to perform detailed chemical analyses of the rings, testing our ideas about metallicity and gas mixing across this new large sample. Gaia can measure the tiny, proper motions of stars within the nearest ring galaxies, giving us the first true 3D maps of their expansion, confirming their dynamics beyond any doubt. This multi-wavelength, multi-messenger approach will transform these beautiful objects from mere subjects of curiosity into essential tools for probing the fundamental physics of galaxy evolution, dark matter, and the life cycles of stars. The coming decade will not just add to our knowledge of ring galaxies, it will finally provide the context to understand their true place in the grand narrative of the universe. Yet all these cosmic wonders, from the violent births to the fading remnants, lead us to a deeply philosophical question about our own place in this grand tapestry. We've explored how ring galaxies are rare, transient phenomena born from specific and unlikely collisions. But what if the universe were different? What if the conditions that create these brilliant rings were far more common, making them a standard feature of galactic architecture? This line of inquiry brings us to the edge of cosmology and philosophy, to a concept known as the anthropic principle, and it forces us to consider whether our very existence as observers is tied to the uncommon quietness of our cosmic neighborhood. The anthropic principle, in its simplest form, suggests that the universe we observe must be compatible with the existence of conscious life that can observe it. We shouldn't be surprised to find ourselves living in a universe with certain properties, because if those properties were significantly different, we wouldn't be here to notice. When we apply this reasoning to ring galaxies, the implications are striking. Our Milky Way is a relatively quiet, stable spiral galaxy. It has not undergone a major merger for billions of years, allowing for long periods of peaceful stellar and planetary evolution. This stability is often cited as a crucial factor in allowing life to arise on Earth. A predictable environment with a steady rate of star formation and a low probability of nearby sterilizing events like supernova provides the long-term stability necessary for complex chemistry and biology to develop over eons. Now, imagine an alternative universe where galactic collisions are 10 or 100 times more frequent. In that universe, ring galaxies would be commonplace, glittering everywhere we look. But that dazzling sight would come at a terrifying cost. A planet forming in a ring galaxy would be subjected to an environment of relentless violence. The constant barrage of ultraviolet radiation from massive stars, the high probability of a nearby supernova explosion within a few million years of a planet's formation, and the gravitational upheavals from frequent close encounters would make it incredibly difficult for life to gain a foothold, let alone evolve to complexity. The very processes that create the ring's breathtaking beauty are profoundly hostile to the delicate, long-term processes that we believe are necessary for life. In such a universe, the skies might be filled with more spectacular vistas, but there would likely be no one there to look up and admire them. This is not to say that life in a ring galaxy is absolutely impossible. Life, as we do not yet fully understand it, might be more resilient than we think, perhaps on a moon orbiting a gas giant that was flung into a quieter part of the ring, or in the shielded core of a planet with an exceptionally strong magnetic field. Organisms could survive. But the odds would be stacked immensely high against the emergence of intelligent, technology-building civilizations that could gaze upon their galaxy and comprehend its structure. The gradual, cumulative process of evolution that led to us likely required the cosmic peace and quiet that a galaxy like the Milky Way provides. Therefore, the rarity of ring galaxies is not just an interesting astronomical statistic. It might be a prerequisite for our own existence. The fact that we live in a universe where such magnificent structures are the exception rather than the rule could be a direct consequence of the fact that we are here to ponder the question. We are, in a sense, living evidence of a universe that is, on the whole, relatively stable and gentle, at least on the galactic scale and over billion-year timescales. The silence of our night sky, punctuated by the steady glow of familiar stars, is not a boring default. It is the very condition that allowed a species to arise capable of building telescopes to discover the violent, beautiful chaos happening in the distant depths of space. Our ability to study ring galaxies is thus a product of the very cosmic calm that they so dramatically disrupt. And so we arrive at the final entry on our list, a galaxy that seems to gather all the mysteries we have explored and weave them into a single, profoundly baffling object. Designated as SDSS J158894 plus 344049, but known to astronomers by the far more evocative nickname, the Great Annihilator, this ring galaxy doesn't just present one puzzle. It presents a cascade of contradictions that challenges our understanding at every turn. Discovered only in the last few years through deep sky surveys, it initially appeared as just another faint smudge. But when astronomers pointed the world's most powerful telescopes at it, they uncovered a celestial riddle of staggering complexity, a structure that seems to break multiple rules of galactic physics simultaneously. The first and most striking anomaly is its appearance. At its heart lies a bright, compact core typical of many galaxies. Surrounding this is a brilliant blue ring of young stars, confirming a recent burst of star formation. So far, so normal, but then, encircling this inner ring is a second, much larger and fainter ring, glowing with the distinct reddish hue of ancient stars. This double ring structure alone is rare, but what makes the Great Annihilator unique is the stark age difference between them. Spectroscopic analysis reveals that the outer, red ring is billions of years older than the inner, blue ring. This is the age inversion phenomenon we discussed earlier, but pushed to an extreme. It suggests a history of multiple, distinct epochs of violence separated by an almost unimaginable length of time. A story written in concentric circles where the outer chapter is far older than the inner one. But the true enigma lies in the galaxy's motion. By carefully measuring the Doppler shift of light from each ring, astronomers made a discovery that defied all expectations. The two rings are rotating in perfect, stable orbits, but they are spinning in opposite directions. The inner blue ring rotates clockwise, while the outer red ring rotates counterclockwise. This counter-rotation is the kind of configuration our models suggest should be violently unstable, yet here it is, a cosmic yin-yang symbol on a galactic scale. The dynamical friction between these opposing structures should have caused them to collapse into the center long ago. Their continued existence implies that the dark matter halo holding this galaxy together must have a highly unusual, perhaps triaxial shape, providing gravitational pockets that can somehow lock these opposing motions into a permanent, albeit precarious, balance. The mysteries deepen when we look at the very center of the Great Annihilator. Observations in X-ray and radio wavelengths reveal an immensely powerful active galactic nucleus, a supermassive black hole in a ferocious state of feeding. This torrent of energy should be blowing the galaxy apart, quenching star formation and dispersing the gas needed to sustain the rings. Yet, the inner blue ring shows no signs of being disrupted. In fact, it appears to be thriving. This suggests that the same Aegean outburst might be simultaneously suppressing and compressing the gas in a delicate feedback loop we do not yet understand. Furthermore, gamma-ray telescopes have detected a faint but persistent and anomalous glow from the galaxy that some theorists cautiously suggest could be a signature of low-level antimatter production, a possibility that, while highly speculative, adds another layer of profound mystery to this already unparalleled object. The Great Annihilator, therefore, stands as the ultimate challenge for modern astrophysics. It is not merely a ring galaxy. It is a cosmic palimpsest that combines the age paradox of double rings, the dynamical improbability of counter-rotation, the violent feedback of a powerful Aegean, and the potential whisper of exotic physics. No single simulation has yet been able to recreate its full suite of properties. Its very existence forces us to consider that our current understanding of galaxy formation is still a rough sketch. Does it represent a series of coincidences so rare it is virtually unique in the observable universe? Or is it a signpost pointing toward a more complex reality, where dark matter behaves in ways we have not anticipated, and where galaxies can endure cycles of creation and destruction far more intricate than anything we have yet imagined? This one enigmatic ring, a perfect circle of contradictions suspended in the dark, reminds us that for every question we answer about the cosmos, the universe is always ready to present us with a deeper, more beautiful, and more bewildering mystery. From the perfect symmetry of Hoag's object to the chaotic dance of counter-rotating rings, from the phantom echoes of dark matter to the stellar baby boom of the Cartwheel Galaxy, our journey through these 50 strange phenomena reveals a universe of breathtaking diversity and profound mystery. Ring galaxies are far more than just beautiful accidents. They are cosmic crucibles where the fundamental laws of physics are tested under the most extreme conditions. They challenge our ideas about gravity, dark matter, and stellar evolution, forcing us to revise our models again and again. Each one is a natural laboratory, offering a unique window into the violent, creative, and endlessly surprising processes that shape the cosmos on its grandest scales. So, what can you do now that you've glimpsed these wonders? The exploration doesn't have to end here. I encourage you to dive deeper on your own. Go online and look up the raw, breathtaking images from the Hubble and James Webb Space Telescopes. Search for Hoag's object, the Cartwheel Galaxy, or any of the other celestial marvels we've discussed. See their perfect circles and intricate structures for yourself. Let the reality of these distant islands of stars sink in. And as you do, I'd love to hear from you. Which of these 50 strange phenomena captured your imagination the most? Was it the impossible polar rings, the ancient cores younger than their surrounding rings, or the ghostly whispers of potential antimatter? Share your favorite in the comments below. Your curiosity